So I will start. Okay. Now the first question is going to be, they say radium. Okay, it's a group 2 element. So the predicted lattice energy for radium sulfide is going to be negative 2612. Yeah. Define the lattice energy. Okay. So when you define lattice energy, we define lattice energy in terms of enthalpy change. Okay, enthalpy or energy change. Okay, enthalpy change. Okay, when 1 mole of normally it's ionic solid. Yeah, so 1 mole of ionic solid is formed. Okay, from its gaseous ion. Okay, under standard condition. So do remember, always you include under standard condition. Yeah, but that standard condition is not going to be the determinant. Okay, for the marks. Okay, the one that is going to give you the marks. Yeah, is going to be, in this case. Yeah, this is the 1 mole of ionic solid is going to be 1 mark. Okay, and it is formed from its gaseous ion, that is going to be another 1 more mark. Yeah, so that is going to be the 2 marks that is going to be allocated for you. Yeah, so the next question over here is, this is similar to your paper 4.1. Okay, they have given you some data about radium and sulfur. Yeah, select relevant data and use it to answer. Yeah, so let's actually answer here. They say that write an equation for the process corresponding to second electron affinity of sulfur. Yeah, so second, it means they already accepted 1 electron. Yeah, so they need to accept 1 electron to give you S2 minus. Okay, second electron affinity. And if you look at the definition of electron affinity, which was asked in paper 4.1, the definition is going to be enthalpy change when 1 mole of electron is added into its ion or atom under standard condition. But the ion or atom must be in gaseous form as well. Yeah, so that is going to be asked in paper 4.1. Okay, so you need to include gases, and also produces at ions in form of gases as well. Yeah, so this is going to be the very important. Very important. And then they say that sulfur they exist in form of S8 in the solid state. Use the question data to calculate the enthalpy change of for this reaction. Now this reaction is similar to the question that we did in paper 4.1. Yeah, for those who have done, this one will look familiar. Because for paper 4.1, they say that they use oxygen. Yeah, here they are going to use sulfur. So if you have done that, this one, roughly you will get an idea what to do. Yeah, and without thinking so much, you know that you need to use this data, and you will know that you need to use these 2 data. This one, you can only know if you do the past year paper, the paper 4.1. Yeah, if you don't know, then revise. Yeah, so I'm not going to explain in detail from the beginning. Yeah, so the first electron affinity of sulfur, if you write down the equation, the first electron affinity is going to be sulfur. Must be in gaseous form. They add electrons, so they will get S minus gas. That's the equation. And then the second is going to be S minus gas. You plus another electron, they will give you S2 minus, which is gas. So what you can do is you can combine these 2 equations. You can combine these 2 equations where you can have you can add them. When you add, the S minus and S minus will be cancelled. So you will have S gas, electron and electron, you will get 2 electron to give me S2 minus, which is gas. Okay, if I do this, okay, of course I need to add these two. Yeah, so I will get 332. Yeah, if you calculate 532 plus negative 200, so you will get 332. Yeah, 332. I'll just put it over there. So now, okay, I will bring this data, okay, whatever that I have over here. Okay. Okay, I will bring this over here. Okay, and then, okay, what I want, okay, is going to be this. Okay, I want to get this. So this one, okay, is going to be related to this particular equation. So I will rewrite this equation: 1 over 8 S8, okay, solid, plus 2 electron. They give you S2 minus gas. Okay. So this one, okay, I will erase first 332. Okay, 332, I put it here first. Okay, and this one is 555. Okay, so again, okay, we need to be very specific. Okay, what we want to achieve over here. I want to have S8 solid to be on my left hand side. Okay, so it is on my left hand side, so it's still okay. But I want the 8S, okay, sulfur, okay, in form of gas, okay, to exist on my right hand side. Yeah. So if you look at here, okay, this is still going to be on your left hand side. Yeah. And then they want 8S. So what you can do, you can times 8 and you turn the equation around. Okay, so if I times by 8, okay, this one, it means this one is all 8, this is 16, okay, this is 8. So I just need to turn the equation around. Okay, if I turn the equation around, it's 8S2 minus gas. It's going to give me 8S gas plus 16 electron. Okay, and then this one, because I turn it around, then it will become negative 332 times 8. Okay, so I can remove this part here. Done. The next part, okay, is going to be, you want S8 alone, okay, you want S8 alone. Here I have 1 over 8, I don't want, yeah. So I times everything by 8 also over there, okay. I times 8, what happens, okay, this will become 1, okay. I times 8, then that will become 16. So 16, I times 8, so you will get this. Okay, so don't forget, this one also need to times with 8. So now you just need to add these two equations. Okay, what you will get, okay, similar with what you have done earlier, yeah, paper for 1. So this 16 electron and this 16 electron will be gone. Okay, and then you can remove, okay, you can remove the 8S2 minus and 8S2 minus. So in the end, what do you get? Okay, you have S8, which is going to be solid. They are going to give you 8S, which is gas, which is what we want. Okay, which is what we want. So what is going to be the calculation over there? Okay, the calculation is going to be, you just need to add this. That is going to be the enthalpy change that we are looking for. Yeah. So if you calculate that, okay, I have done it. So I'll just make it bigger. Okay, I have calculated for you. So you just need to have 555 times 8. Okay, plus with negative 332 times 8. Okay, if you calculate, okay, you will get this value 1784. Okay, so you just need to put positive 1784. Make sure, yeah, you put positive, yeah. So that is going to be the answer, okay, for this question. Okay, so if you move on, okay, so they are asking you to calculate the standard enthalpy change of formation of radium sulfide. Okay, this one, okay, so just to minimize distractions over here, I'll try to erase a little bit here. I think this one is important. Yeah. So I took the data, the one that I calculated just now, S8 solid to become 8S, okay, gas, okay. I just put over here just in case 1784. Yeah, just in case if I need on top of all the information that I have over here. I took all this information and I brought it over here. Yeah, so that when I calculate, I can use that. Yeah. Now this is going to be, you can see they didn't give you a lot of room also. Yeah. So if you of course the question has to do with drawing Born-Haber cycle. Yeah. But the intention is not for you to draw a very good Born-Haber cycle or a very complete Born-Haber cycle. Yeah, if they really want you to draw a very good Born-Haber cycle, then they will give you 3 marks and then give marks for that. Okay, what they want is do whatever, yeah, or a sketch or rough diagram. Okay, as long you calculate. For me, the standard enthalpy change is they are okay, something like that. So that is what they want. Okay. So you do not need to follow the from the bottom. You do the atomization, okay, and then you want to do the first ionization energy, second no need, yeah, because there is going to be some shortcuts, okay, similar to paper for one. Yeah, you can use certain shortcuts over here. So if I look at it, it's going to be radium sulfide. So I know radium sulfide is actually formed from radium, which is going to be solid. Okay, sulfide is going to be S, 8, okay. So half, must be must be in solid form also. Okay, so they use the solid form. Okay, so once you have this, half S8. So what you are going to get, in the end, they are forming, I am assuming first, yeah, because enthalpy of formation can be either positive or negative, yeah, but I'm assuming, I'm assuming it's negative. Assume only lah, okay. If it is positive, later I can erase and draw again, no problem, yeah. So I'm assuming its formation is negative. So I'll just say this is Ra, S, so solid. Okay, radium in solid. Okay, so S8 is going to be in solid form. Okay, and then they give you Ra as solid. Yeah, that is enthalpy of formation. Yeah, enthalpy of formation. So normally what we do is, we keep on going up. Okay, and normally we try to change them into gas, which is going to be atomization and so on. But yeah, you can eliminate certain steps. Okay, because you can see that, they say here, RAS to become Ra2 plus gas. They already combined so many things. Yeah, they have already combined atomization. They have combined first ionization energy. They have combined second ionization energy. So you can just simply write down. Okay, no need to write everything. Okay, you just straight away write down they are producing Ra2 plus and 2 electron. You just need to put the gas. Okay, and still, you still have the half S8 in solid form. Okay, so this value is going to be 1619 positive. Okay, next step, is going to be, of course, the next step is going to be related to sulfur. Yeah, related to sulfur. So if you look at related to sulfur, no need to atomize because I don't see any kind of information, other than this, the one that you calculated. You have this 1784, which is going to be suitable for the atomization, but you do not need to use that, because they have given you this, which is a combination of atomization, and electron affinity, and they have combined first electron affinity, second electron affinity. That means you do not need to use this, you do not need to use this. They have combined for you. So normally we say first is going to be the first electron affinity, is going to be positive, negative, and then the second electron affinity is going to be positive, but you do not even need to show that, yeah, because they have combined that over here. So you just need to show it's positive. So I just say because there is a presence of electron, yeah, and I know that from here to here, okay, the 2 electron is coming from here. So I have Ra2 plus, which is gas, okay. After they react with the electron, okay, I know that they are going to give you S2 minus, which is gas. So this entire process is 555. I have saved my time, yeah, based on what they want. That is what they want, actually. You don't go and use all this data again and draw and waste your time. Yeah, don't go and do that. Okay, this one, if you ask me, this one is for nothing. Okay, so they just simply give. Yeah, so once you have that, okay, we know that after, okay, you get the gaseous ion and you form the solid, that is going to be your lattice energy. Yeah, so now I need to determine whether my hydration is going to be negative or positive. So how to do that? Okay, quite simple. Okay, lattice energy they have given negative 2612. Okay, 2612. And you know that, okay, this information, which is going to be this, okay, this, and this, the enthalpy of formation, okay, must be similar or must be the same, the total must be the same as this, okay. One is actually going up, okay, but the number must be the same, left and right, the number must be the same. This, okay, and this must be the same, okay, then only it makes sense. So if I count, okay, this is going to be 2612, which is negative. It's okay, just take the value first, yeah, 2612. If I add 555 with 1619, okay, if I do that, okay, I will get the value which is going to be 2174, okay, without including, okay, formation. Now from here I know, okay, I know that my enthalpy of formation is going to be negative because it's this value, okay, is smaller than this value. It means that, okay, your enthalpy of formation must be going down. Okay, if it is different, okay, if it is different, then I have to erase this part, okay, the enthalpy of formation, and I need to bring it up. Okay, in this case I no need to do that, yeah, which is consistent. Okay, so I know, okay, my enthalpy of formation is negative. Okay, so what I need to do is just to compare. Okay, I just need to find what is the difference of energy over here. So I just put 2612, you minus 2174. Okay, I will get the value of, okay, I will get 438. Okay, 438. Okay, so now whether it's negative or positive, okay, you look at the diagram. Okay, this one is going down, must be a negative value, which is 438. Okay, this is how you get the value. Okay, of course you can use different methods, okay, which is the one that I taught you, clockwise equals to anti-clockwise. Use a normal Born-Haber cycle and so on, you can get, yeah. But this one, okay, I teach you the easiest way, yeah. This is the easiest way, which is going to be, you can straight away get negative 438 as your answer. Make sure it's negative, yeah. How do I know it's negative and positive? It depends on these two values. Okay, so if let's say, okay, this value is bigger than this value, it means that, okay, you need to draw the enthalpy of formation up. Okay, so it will go up. So that enthalpy of formation is going to be positive value, yeah. So in this case, okay, I can only show you from here, so I'll just tell you, yeah. So this one is going to be negative 438. Now the next question is, state the two major factors, okay, that affect the numerical magnitude of lattice energy, yeah. So lattice energy, please remember, okay, it depends on your charge density. So what is charge density? Okay, charge density is measured by, okay, we never gone in detail about this, okay, but I think it's important. Yeah, charge density is going to be the product, actually it's the product of the charges, okay, you times, okay, it's a product of the charges, and then divided by your ionic radius, yeah, the radius, but the radius, okay, must be plus, okay, not times, okay. So this one is going to be plus, okay, it's a sum of the radius, okay, but it's not important. Yeah, what is important is you need to know it's going to be charge divided by radius, okay, that is charge density, okay, charge divided by radius. So here, okay, when they say state the two major factors, yeah, if you just write down charge, if you just write down radius, it's okay, okay, but it is not the same as the marking key. So our aim of doing this is to make our answer similar or closer to the marking key so that we can get the marks. That's the reason why we are doing past year paper. Yeah. So the charge density is going to be, instead of just putting charge, okay, we need to put ionic charge. Okay, please remember ionic charge. And okay, if you don't want to put the ionic charge, you want to go in detail, okay, the in detail is the products of ionic charge, okay, so the products of ionic charge, okay, they times, yeah, the product products of ionic charges, okay, and another factor is going to be your ionic radius, yeah, but the ionic radius, okay, we can actually write down the sum of ionic radius. Okay, don't get me wrong, if you just write down as ionic radius, it's good enough, okay, you will get the mark, okay, ionic charge, okay, ionic radius, I think that is enough, yeah, but we want to learn more, yeah, so I'll let you know, okay, these are the two factors, products of ionic charges and sum of ionic charge, ionic radius, okay, for each factor that you have identified, okay, state whether it tends to make the lattice energy of radium sulfide more or less exothermic. Yeah, this one is very important, okay, because we need to know your lattice energy is always going to be negative. Okay, for those of you who do not know about this, you know now. Yeah, lattice energy is always going to be negative. Why? Because you are bringing in the gases ion together, so it's a bond formation. Okay, so lattice energy, okay, is always going to be negative. Okay, whether they are less exothermic or more exothermic depends on the type of bond. If they form a stronger bond, then they are going to have a higher exothermic, more energy is going to be released. Okay, so this one is affected by the charge density. Yeah, so if let's say you have more charge, okay, it means more attraction. Okay, it means that they will release a lot of energy. Okay, if you have a smaller radius, okay, smaller radius, they are going to be the nucleus will have greater attraction, yeah, because smaller, there is no shielding and so on, so they are going to actually form more bonds, so they will actually give more exothermic reaction. So in this case, okay, we just want to compare, okay, radium sulfide Ra2 plus, okay, S2 minus. Okay, I am going to compare with sodium Na plus and Cr minus. So first thing that you notice over here is going to be the charges. Okay, you can see this will have, okay, if you follow the charge, this one, okay, is going to be having greater charge, okay, ionic charge, therefore they are going to form more attraction. Okay, the 2 plus and 2 minus, they are going to be more attraction, they are going to be more exothermic. So I will just say, okay, for Ra, okay, for RAS, okay, has more, okay, exothermic lattice energy because the charges or the ionic charges or the product of ionic charges are greater than NaCl. Okay, so that's the first point. But okay, they say that you need to also compare. Okay, when you compare related to atomic, ionic radius, okay, radium, okay, is group 2, but they are at the bottom of the periodic table. Yeah, you can refer. Okay, and we know that this is also sulfur. Okay, chlorine is at the top. Okay, sulfur and chlorine, I think the difference is not that much. But if you compare sodium and radium, okay, I can actually clearly see that sodium is at the top, okay, of group 1. Okay, radium is going to be at the bottom of group 2. Yeah, so we can say that the radius is another factor. Okay, so the ionic radius, okay, the ionic radius of RAS, okay, Ra2 plus and S2 minus, okay, is, okay, greater than Na plus and Cl minus. Okay, if they are greater, okay, what I can say is, okay, we know if this is greater, the charge density is going to be less. Yeah, so it means the attraction is not going to be that great. Okay, so okay, we can say making, okay, less attraction with the opposite charges. Okay, therefore the lattice energy is less exothermic in terms of, okay, in terms of ionic radius. Then now, okay, now they're telling the lattice energy of sodium chloride and radium sulfide. Okay, they say radium sulfide is going to be this one. Okay, more exothermic. Okay, I told you that radium sulfide, they can have, according to our previous answer, okay, they can either, okay, they can have, okay, the more exothermic, or they can also have less exothermic. Okay, but in this case, they are focused on having more exothermic, which is this. Yeah, so they say that identify the dominant factor. Yeah, the dominant factor in this case, is it the ionic charge or is it going to be the radius? Yeah, so in this case, you know that, okay, since this is going to be the one that they focus, it means we are talking about the dominant over here is the ionic charges. Okay, so identify the dominant factor. Okay, is going to be ionic charges. Okay, and if they ask you why, okay, explain your answer. Okay, because, okay, the lattice energy, just need to tell the lattice energy of RAS is more exothermic. Okay, because it's more exothermic. Okay, therefore, okay, the ionic charges is the dominant factor. Okay, so that is how you explain for question number this question. Yeah, 1 mark. that okay, Ashley? Yeah. So let's actually move on. Okay, question number 2. Okay. So you see, okay, very slow and steady. I think if I started 8 minutes late just now, so maybe 30 minutes for one question. Yeah, relax. Yeah, just relax and so on. Okay, I find it better. Yeah, I find it better and it's not too rushing. Okay, so here, okay, so if you look at question number 2, okay, this is going to be KPC, okay, partition coefficient. Yeah. Okay, so you have ethoxyethane, okay, can dissolve in both water and octane 1-ol. Yeah, the expression and the numerical value of the partition coefficient, okay, of ethoxyethane, okay, between these two, okay, are given. And of course, if KPC, it means the partition coefficient, they must be between two immiscible liquids, okay, and they say that water and octane 1-ol are immiscible. So they say that, okay, if you calculate the KPC, yeah, so they have mentioned that you put the ethoxyethane in octane 1-ol and then you divide, okay, the ratio with octane 1-ol in water. They found out is 6.760 at 20 degrees Celsius. They found out that value. Then this in one experiment, okay, they take octane 1-ol, they try to recreate that experiment. Okay, they put the octane 1-ol at 20 degrees Celsius. They add into to a solution of ethoxyethane in water. So basically, ethoxyethane in water will start to dissolve in octane 1-ol also. Yeah, at 20 degrees. So you can see the temperature is still the same. Okay, the mixture is analyzed immediately. Yeah, and a value of KPC is calculated. Okay, you can look at the key point immediately. Yeah, this is the main key point. Yeah, the calculation is performed correctly. The value calculated, however, okay, is lower than expected. Okay, we expect KPC supposed to be 6.760, but you get a lower value. Yeah. Now we need to explain why the value is not the same. Yeah. Any idea, anyone?
Because they do it immediately, it doesn't have time to dissolve in octane 1-ol.
Okay. Have you tried this question before?
No.
Okay, good. Okay, if you can get this, okay, then it's very good. Yeah. So, but you need to make some changes a bit in that answer. Yeah, in order to get the mark. Okay, basically they are doing it immediately. You are using KPC. What actually happens is, okay, you need to allow time, okay, for them to reach equilibrium. Yeah, the movement. Yeah, so it must reach an equilibrium. So if you just calculate directly, it means that the equilibrium has not been achieved. Yeah, so that is the term that we supposed to put. Yeah, why the value calculated less than 6.760? Because, okay, because it is analyzed immediately and not allowed to reach the equilibrium. Okay, you need to actually allow some time for it to reach equilibrium. So now they're still reacting. Okay, they're still moving. Yeah, so they are not allowed to reach equilibrium. So you need to still tell more about this value. Why is less? It means now, okay, remember the ethoxyethane was still in water. Okay, was still in water. So if you have 5.625, it means that, okay, this value is still more. Okay, this value is supposed to get 6.760. Okay, but when you calculate, okay, you are going to get a smaller value. If it is smaller value means this value, okay, divided, yeah, by that value is big. Yeah, that value is big. Then only you will get a smaller value. Yeah, so it means that they are still the ethoxyethane. There are a lot of ethoxyethane still in water. Okay, so you need to tell that they are high concentrations of ethoxyethane in water, that has not been able to mix to octane 1-ol yet, making the value of KPC smaller than 6.760. So please relate. No need to be exactly the same, but the idea must be there. It didn't reach equilibrium yet. Didn't. But just don't say it is analyzed immediately. That's the reason. No. That will not give you the mark. It is not allowed to reach equilibrium yet. Now, a second experiment, this is the experiment that they did it correctly. They performed the experiment, and then the value of KPC is found 6.760, which is they managed to get. It means they reach equilibrium. The concentration of ethoxyethane, in octane 1-ol layer is 7.62 gram per dm cube. Now, so this one they found out. So they say this is going to be the concentration. So calculate the concentration in gram per dm cube of ethoxyethane. For this one, normally we calculate in terms of mole per dm cube. But for this one, doesn't matter if you calculate in mole per dm cube or gram per dm cube, because it is involving the same octane 1-ol. But it's okay if you are still confused and so on. It's okay. We can still go on. I'll show you. So what is important over here is they put the 6.760 is going to be equals to the concentration of the ethoxyethane in octane 1-ol. So ethoxyethane in octane 1-ol is 7.62. So I write down 7.62 gram per dm cube. So now let's say I want to change it to into mole per dm cube. What I need to do, I just need to divide by the MR. The MR for ethoxyethane, you can see is going to be C4H10O. So that's going to be 48 plus 10 plus 16. So that's going to be 74 if you calculate. So the MR is 74. So if I put over there, if I just put 74, and then I'm assuming the volume is 1 dm cube. So this is going to be in number of moles. Number of moles. And then if you look at the number of moles, in form of the ethoxyethane in aqueous layer, we want to find out what is in gram. Let's actually focus on how many gram. X. Same. Mole per dm cube. So you always divide by 74 also. You change it into mole. Now, why I said that is not important, is because 74 and 74 will cancel. It will cancel. So not all the time we can use this. For this question, yes. You can just straight away use in gram per dm cube, which is going to be 7.62. Divide by X. Is going to be 6.760. You can find what is X. X, you will give you the answer in gram per dm cube. So 7.62 divided by 6.760. You will get the answer, which is going to be 1.127 gram per dm cube. And I want the answer in 3 significant figures. I will write down 1.13 gram per dm cube. Straightforward. So no need to worry so much about mole and so on. Is that, yeah? Then now, okay, you are taking 100 cm cube of octan 1 layer. So we know, okay, we know that in 1 dm cube, okay, just now we calculated in 1 dm cube, okay, octan 1 layer, you see octan 1 all layer is 7.62 gram per dm cube. 7.62 gram per dm cube. From there, okay, from there, you are taking 100 cm cube. Okay, you're taking 100 cm cube. Just imagine that's the concentration in 1 dm cube. Yeah, in 1 dm cube, you have 7.62 gram. And you are taking 100 cm cube. Okay, so if you're taking 100 cm cube, means you are taking actually 0.762 gram. Okay, I hope you know this. Yeah, so in 1 dm cube, you are taking 7.62. Okay, if you take 100 cm cube, okay, it's 1/10. Yeah, 1/10. Okay, so you are taking this amount only. Okay, and you shake it with 100 cm cube of water. Yeah, calculate the maximum amount, okay, in mole. Okay, so now they mention in mole. So what I do, okay, is going to be, okay, you just the same condition, they are going to follow 6.760. And okay, we are going to look at the concentration in okay, in octan 1 all. Okay, so concentration in octan 1 all, okay, you took the 100 cm cube, so the concentration is 0.762 gram, okay, divided by 74, okay, that's mole. Yeah, that's mole. And then you still want the concentration, so that's going to be divided by 100. Okay, so divided by 0.1 dm cube. Okay, this is the entire concentration. Okay, but do remember that is not the full version. You just take, yeah, they haven't dissociate or mix yet. Yeah, so imagine now the one that is going to mix, okay, is going to be X. Okay, it means the one that will dissolve into the water. So what I can do is, okay, I can just put minus, this is the number of moles, okay, number of moles, the overall. Okay, let's say the number of moles, okay, that I want is minus X. Okay, the one that go into the water, put minus X, divided by the one that went into water is X. Okay, number of moles. And then also remember that is going to be divided by 0.1, which is 100 cm cube of water. Okay, what I can do over here now is, okay, I can cancel this and this. Okay, I can cancel. And okay, I can have this value, which is going to be 0.762 divided by 74. Okay, minus X. Okay, divide by X. Okay, so if I times the X to there, I will have 6.760X. Okay, so if you calculate this, okay, 0.776, okay, 0.762 divided by, hold on. Can you guys calculate for me this? 0.762 divided by 74. I don't think so I have that data. Or is it 0. Yeah, just help me to calculate this. So if I bring this over here, you will get 7.760x. 0.762 divided by 74. Still in moles. Yeah, still in moles. X is going to be 0.762 divided by 74. You divide with 7.760. Okay.
I got 1.33 times 10 to the power of -3.
Yeah. I get the same as well. What I did, okay, my previous working, I count according to the mass, yeah. Then I did change them into mole. That is also possible. You will get the same answer, yeah. So here, okay, I put it in moles, okay, and then I calculate, okay. So you will get the same thing, 1.33 times 10 negative 3. Both of the ways it works. Okay, see which one is suitable for you. But the idea is, okay, you need to represent it by minus x. Okay, minus x divided by x. Okay, next question. So an aqueous solution of lead-2 nitrate is mixed with aqueous solution of sodium iodide. A yellow precipitate of lead-2 iodide is formed and filtered out. So I've written the equation over there. Okay, so you have PbI2, which is solid, then sodium nitrate. Okay, but they say that leaving solution X, it means sodium nitrate is there. Okay, together, maybe with the excess of this solution, yeah. So there are some other Pb2 plus, they are still I minus, so that is the solution X. That's why the solution X, okay, they contain, okay, this concentration of Pb2 plus, and it contains this concentration of I minus. Then they gave they have given you some information. They say use this data, okay, to calculate the value of KSP. Yeah. So if I want to calculate the value of KSP, okay, we know that KSP is going to be, if you have PbI2, which is the solid, okay, they are going to give you Pb2 plus and then 2I. Okay, so if I want to find the KSP is going to be Pb2 plus concentration and then I minus to the power of 2. Okay, only the products, yeah, only the products. So I have all the information that I need, because that is the information that they ask you to use, yeah. So I'll just straight away use that information. They have given me 5.68 times 10 negative 3, I just put it in, and then 4.2 times 10 negative 4, I just put that in, and to the power of 2. Okay, if I do that, okay, I will get the KSP value. You can calculate. You will get 1.00 something. Then in the end, I've simplified that to become 1 times 10 negative 9. Okay, so 1 times 10 negative 9. You can see this is mole per dm cube. Mole per dm cube to the power of 2. So in total, you'll have mole to the power of 3 dm negative 9. Yeah, so mole 3 dm negative 9. Okay, so you just need to put that. Okay, then they said, okay, they said that potassium iodide, don't get confused, this is lead iodide. Okay, so you are adding potassium iodide, Ki, okay, in water, and then describe what will happen, okay, if a few drops of potassium iodide are added to a portion of solution X. Okay, we know there is this is a KSP. Okay, when you have KSP, okay, if you just take this particular equation, okay, and just copy this and put it over here. If you take that equation, okay, when you add the Ki, what are you doing? You are just increasing the concentration of the I minus, okay? And what will happen, okay, to eliminate this I minus according to LCP, you need to shift the position of the equilibrium to go to the left-hand side. Okay, that is going to cause, okay, formation of precipitate. Okay, remember I told you, okay, I want to actually open a restaurant, seafood restaurant, and because I want something that is going to form more precipitate and so on. If you can remember the calcium carbonate related stuff, yeah. So it's similar to that. Okay, that is the concept that I taught you, is what we call as common ion effect. Okay, so that should be mentioned. Yeah, that should be mentioned. So you just say, okay, the addition of, okay, the addition of Ki, okay, increases the concentration of, okay, I minus, which will give the common ion effect okay, common ion effect, which makes, okay, the products of concentration of Pb2 plus and then the I minus to the power of 2 greater than Ksp. Okay, it makes it greater than Ksp, which makes more precipitate of Pbi2 to be formed. So Pbi2, okay, they have mentioned that, okay, is a yellow precipitate. So what is seen? Explain what is seen. Yellow precipitate is formed. Formed and seen. Yeah, so that's going to be the total marks for that. Yeah, so 2 questions, yeah, in 1 hour. Okay, so that's it from me. Yeah, so I will stop recording. Okay, let's start now. Pure water is a very poor conductor of electricity. Okay, however, okay, they said hydrogen chloride dissolved in water, ions are formed, and current flows during the electrolysis. Okay, the overall change, okay, they have given you this information, they have given you this information. Okay, but this question, okay, if we have done paper 4.1, this question is similar to that, okay, that they are asking you. In that paper, they ask about hydrogen gas. In this paper, they are asking about chlorine gas. Yeah, that's why it's good to do the past year paper. You can actually know what they roughly are asking. Okay, if you ask me, this entire thing doesn't mean anything. Okay, they just give you some information. Okay, for those who don't have any idea, just to make you to get confused. Yeah. But yes, you still need to read. Yeah, that doesn't mean that you don't need to read. Okay, they say that, okay, certain amount of current is passed through for a couple of minutes. Y minutes, 351 cm cube of chlorine are produced at anode. Yeah. So this is the main information. Okay, so what is important is to use the main information and follow through the question. So calculate the number of chlorine molecules produced during electrolysis. Okay, this one, okay, we know that 1 mole of any gas, they are going to occupy 24 dm cube. Okay, so we know that, okay, if you have 1 dm cube, then you are going to get 1 over 24 mole. Okay, so here I am dealing with 0.351 dm cube. You have to divide by 1000. Yeah, so if you have for this volume, so how many moles? Okay, this is going to be 1 over 24 because 1 dm cube is that. So you just need to times, okay, with 0.351. You will get the number of moles, okay, number of moles of the chlorine molecules. Okay, of chlorine molecules. So V1, okay, V1 the molecules, okay, not the number of moles, okay, and we know that 1 mole, okay, 1 mole is going to be 6.02 times 10 to the power of 23. Okay, you just need to take this value that you get, you times with 6.02 times 10 to the power of 23. Okay, and you will get the value. Okay, if you calculate, okay, you can see my working. If you calculate all that, okay, you will get this value, 0.08804 times 10 to the power 23. I have simplified that. Okay, I bring it over here. Okay, 10 to the power 21. Okay, 8.80. Okay, I will use 3 significant figures. Okay, so 8.80 times 10 to the power of 21. Do remember it's a molecule, yeah? Okay, sometimes they can change this question, number of chlorine atoms. then you still need to times another 2. Yeah. So this is going to be molecules. So we just leave it like this. Now, after that, calculate the total number of electrons transferred. This is the part that I told you. It is similar to what we have learned in paper 4.1, okay, which is they are asking you about the number of electrons. Okay, for this, you do not need to worry about these two equations. Okay, you just need to write the equation at the anode, which is going to be Cl minus, okay, minus electrons. So it's going to become Cl2, okay, plus 2 electrons. So this one will be this. Okay, so from here, okay, we know that every 1 mole of Cl2, it's going to give, it is going to involve 2 electrons. Okay, so it's a transfer of 2 moles of electrons. Okay, so double, and you have calculated this is going to be number of moles of the molecule. So you just need to double, you just need to times by 2, 8.80 times 10 to the power of 21 times by 2. Okay, because this, okay, 2. So once you times by 2, you will get this value. Okay, I calculated for you, 1.76 times 10 to the power of 22. Those who haven't calculated, you have your calculator, you can calculate, yeah, together. Yeah, you still have time. Okay, you just try to calculate and check, yeah, whether you have the correct answer as mine. Yeah, but do be very careful. Okay, we want 3 significant figures. Okay, even though in your marking key they have mentioned 8.8. Yeah, 8.8 is not 3 significant figures. Yeah, 8.80 is going to be 3 significant figures. It should be 3 significant figures or more. Yeah, don't take the chance 8.804. You just put 8.8. No, don't take that kind of chances. Yeah, so make sure, okay, it's either you write down 8.804. That is better. Yeah, that is better. Okay, but if you have the situation like this, I will always advise you to write down 8.80. Yeah, so the 0 behind will add the number of significant figures. I think let's not talk too much about maths, but do remember 600, okay, is considered to be, okay, 1 significant figure. Yeah, but if you put 600.0, yeah, that is going to be 4 significant figures. Yeah, so please remember this. Okay, you can check, okay, with your maths. Okay, the point, okay, after point, whatever value that you put, yeah, after the decimal, it's all very significant. Yeah, so very important. Okay, next. Okay, calculate the quantity of charge in columns. Okay, the number of the total number of electrons. So if you want to calculate the charge, okay, every 1 electron, okay, they are going to carry this charge 1.6 times 10 to the power of -19. Okay, all this information, yeah, you can get it from the data booklet, but for your syllabus, okay, from now on, they are not going to give you the data booklet. You can look at this value at the end of the paper. Yeah, at the end of the paper, they will give you data book. They will give you the periodic table, and they will give you important constants. Yeah, even like, for example, Avogadro constant, this charge, all these are given. Unless they are not available there, okay, they will give you in the question itself. Okay, if you cannot find the question and you need a value, make sure you check at the end of the paper. Yeah, so that is going to be there. If you are not sure, you still want to find out how it looks like, okay, you look at your what is it called, sample paper. Yeah, hold on. Yeah, I forgot. There is a type of paper that they will give you, which is good. You can find it from the website. Okay, is it sample paper? Something like that, sample paper. If I remember, I will let you know. Yeah. Ella, can you help? Or Ashley, do you know what is the paper called?
Is that the data booklet or?
I just search for formula sheet, sir.
Yeah.
And it will pop up somehow.
Okay, it is inside the website. Okay, It is supposed to be sample paper, but they use a different term for it. Okay, normally Cambridge, okay, whenever there is a change in syllabus, they will take some questions from past year paper, they will create that question, and then they will give you, yeah, specimen paper, correct, Ella, yeah. So you can look at the specimen paper, yeah, the latest specimen paper in your website. Okay, from there you can see how the format will look like. Okay, the format, you will see that that format in your prelims. Okay, so we will use the same format, yeah, which is going to be data booklet will not be given. Okay, you will have all the information in the paper itself. Yeah, good. So let's continue. Okay, if you have this, okay, this is the charge. Okay, they want quantity. Yeah, quantity, no need to put negative. Yeah, so they want the charge in columns. Okay, so you just need to times, okay, 1.76, okay, times 10 to the power of 22. This is the number of electrons. You times with 1.6 times 10 negative 19. Yeah, so you will get 2.816 times 10 to the power of 3. Okay, you want to leave it like this? Good. Yeah, or you can actually give your answer as 2816, column also okay, or you write down your answer as 2.82 times 10 to the power of 3 also can. Okay, but normally this kind of numbers, if I have more numbers, it's better. Yeah, so I will tend to use 2816 column. Okay, so this is my reasoning. Yeah, but if you write down 2820, still accepted. Okay, 2820 is still accepted because 3 significant figures. Yeah, now calculate the time. Okay, y in minutes. Okay, sometimes they like to play around this. Yeah, your formula, okay, q equals to it, is going to measure in form of seconds. Yeah, the time is in seconds. So if you have q you have already calculated 2816. Okay, and then I is given, which is going to be 3.1. So you just need to calculate the time, and the time, if you calculate, you will get 908.387 seconds. Okay, so you need to change it into minutes. Yeah, the common mistake is the student give the answer as seconds and then directly put over that. Okay, but I think every year, okay, they try to help the students, okay, by putting here, reminding them, by putting here, reminding them, okay, by putting it here to remind them, okay. But despite all the reminders, yeah, students still make that mistake. Yeah, so even like sometimes during prelim, we also decide, should we make it bold? Yeah, sometimes you see in the prelim paper, we give fourth reminder, which is we bold the minutes sometimes in some papers. For my paper, I don't bold. Yeah, for my paper, we will follow the actual syllabus. So, but we go to that extent. Yeah, let's actually remind the students some more. Okay, but these are the things that you need to take note. Yeah, because students always make that mistake, especially okay when we are dealing with 2 hours paper and so on. You want to rush. Yeah, students make that mistake. So the time is going to be divided by 60. Okay, you divide by 60, and in 3 significant figures, I have 15.1 minutes. Okay, so let's move on. Now, this is going to be standard entropy. Okay, they are given. Okay, and then we are going to calculate the entropy for the reaction. If you compare with our previous syllabus, the one that we learned under entropy last time, yeah, we did learn extra. Yeah, no, I think for your batch, I didn't teach you extra. Yeah, so I followed the syllabus. Yeah. So last time, okay, this calculation used to be more difficult, more complicated. There are another step. Okay, they have removed it, yeah, to make it more easier. Yeah. So this question is actually based on that. Yeah, you can see that standard entropy are given the table. Okay, they just ask you to calculate the entropy change. If you are calculating the entropy change, okay, the entropy for the product minus the entropy of the reactant. So if I look at the reactant, okay, product H2 and Cl2, you see this one and this one. So I add, okay, then minus the entropy of the product. But the entropy of the product, if you have 2 over there, you need to times by 2. Okay, so minus 2 times of this. Okay, and you will get negative 20, but do remember it's in joule per Kelvin per mole. Okay, this is very important. Check again whether, okay, the unit is in joule or kilojoule, but entropy normally is in joule. Yeah, so you get that, you put the negative 20. But be very careful, okay, when you calculate the Gibbs free energy, Gibbs free energy is going to be, you are going to use everything in kilojoule. So therefore, okay, when you calculate the Gibbs free energy, okay, this one, if you remember the formula, P is not so hot, okay, it's not so hot C, yeah, something like that, like I told you. Okay, so this one, okay, if you use, okay, this value, delta H is given 185, okay, then minus, okay, sometimes they will not give you this one, yeah, as long as you see the standard condition, yeah, it's already 298, okay, in this case they did, okay, they did give you, yeah, if they don't give you, you still need to know it's 298. Okay, and then times with this value that you calculate, but do not take this 100%. Yeah? Negative 20 must be in kilojoule. Negative 20 divided by 1000. Very, very important. Yeah, student always miss out this. Yeah, so this one cancel. If I calculate, I will get a positive value. Okay, which is 191. Okay, you can calculate and check. Yeah, so 191. Okay, positive value. Okay, so make sure don't simply put 191. Okay, change it to positive. Be specific, positive or negative. And involving enthalpy change, you must put positive. Yeah, predict the effect, okay, of increasing temperature on the spontaneity of this reaction. Okay, this one, okay, actually this question should can be better. Yeah, it can be better. Okay, why? Because the entropy change, okay, entropy change is going to be negative. Okay, entropy change is negative, and then we know that delta H, okay, is going to be positive. So this one is going to be, you can see the symbols are going to be opposite, yeah, negative and positive. Whenever you have negative and positive, yeah, if the entropy is going to be negative, delta H is positive, okay, it means that the reaction is non-spontaneous, okay, at any temperature, okay. That should be the answer based on, yeah. Do remember this is I don't think so it's an official marking key yet, yeah, maybe not final, I don't know, yeah. But if you look at if you have delta S is going to be positive and delta H is going to be negative, this is going to be always spontaneous at any temperature. This is what we have learned, okay. So I think, okay, because they are too focused on using this, using the equation, okay, which is delta G equals to delta H minus D delta S, okay. So they want you to use this, yeah. So when you have, okay, increasing temperature, okay, do remember your delta H is, okay, they have given, which is going to be positive. This is a positive value, yeah. When the temperature is increased, okay, when the temperature is increased, we know the delta S is negative. Negative and negative is going to be positive, yeah. And negative and negative is going to be positive. So if you increase that, the value of the Gibbs free energy is definitely going to be positive. Okay, but okay, it is going to be, if you want to compare, yeah, maybe positive 50 and positive 100, they have difference. Maybe that is what they want to compare. Yeah, positive 50 and positive 100, both of them are non-spontaneous. Okay, but if you compare, okay, this one may be spontaneous, okay, then 100. Okay, so maybe they are approaching in that sense. Yeah, so here predict the effect of increasing the temperature. The more bigger this, okay, you will get a bigger number, okay, a positive value. Okay, so it means when T is increased, okay, your minus T, this value becomes, or you can just say this value becomes, I think better negative here. Negative, negative, so becomes more positive. Okay. It becomes more positive. Okay, so Gibbs free energy is going to be more positive, making it less spontaneous. This one I'm answering based on the marking key. Okay, but okay, if you ask me, the best answer will be, okay, even though it's less spontaneous, because you need to mention about this, okay, you can include, okay, you can include, because you know that it's a non-spontaneous at any temperature, so it will be always more than 0. You can include that. Okay, you can include that. Okay, but it is not found in the marking key, this one. Okay, so they are just focused on these two. So that's why I do not know whether the marking key is the final version. Yeah, but if you ask me, this condition, it is going to be non-spontaneous at any temperature. Yeah, so if you just write down non-spontaneous at any temperature and explain why, okay, by saying the Gibbs free energy is always going to be more than 0, that will be a better answer. Okay, next question, number 4. Okay, separate samples, okay, of 0.01 magnesium nitrate and 0.01 strontium nitrate are heated until completely decomposed to metal oxide and nitrogen dioxide and oxygen. Okay, so I've written the equation for you. Yeah, magnesium nitrate, magnesium oxide, NO2 and O2. I have even balanced it for you because I have 2 nitrogen, so I put 2 nitrogen here. So when I look at the oxygen, 6 oxygen, so I have 1 and then 4. Okay, so I need 1 more oxygen, so I still need to put half over here. Yeah, the same thing. Okay, you repeat for strontium. Yeah, so do remember magnesium. Okay, if you look at group 2, magnesium is at the top, strontium is at the bottom. Yeah, so that is going to help us to roughly predict, yeah, what will happen. Yeah, so here, okay, we know that nitrates, okay, if you look at nitrates and carbonates, okay, as you go down the group, this one in AS we have learned. Yeah, as you go down the group, it is going to be more thermally stable. Okay, thermally stable. Okay, but in your A2 we have learned why. Yeah, your ion polarization chapter. Yeah, under lattice energy. Yeah, state which of these group 2 nitrates require higher temperature, okay, before it begins to decompose. Which one is difficult to decompose? Of course, this one, strontium nitrate. Yeah, strontium nitrate. Okay, so I will just make it bigger so that I don't end up writing it again. Okay, strontium nitrate. Okay, is going to be more thermally stable. Yeah, because you talk about the ion polarization. Okay, so if I look at Sr2 plus, okay, it's a smaller cation, or you say Sr2 plus has, okay, smaller ionic radius. I think the one that is preferred in your marking key will be more this one, yeah, has smaller ionic radius. Okay, but it's okay, smaller cation also will be accepted. Okay, because it is smaller, okay, sorry, Sr2 plus is bigger cation, yeah, okay, so my mistake. Okay, bigger. Okay, this is larger. Okay, so if you have larger cation, okay, they are going to be less polarizing. Okay, they are going to be less polarizing. The polarizing power depends on the charge density. Yeah, charge divided by radius. So if you have more charge, more polarizing. Less radius, more polarizing. Yeah. So they have less polarizing compared to Mg2 plus. Okay. So,
Sir,
yep.
what does polarizing mean?
This one refer to your lattice energy. Yeah. Polarizing means if you have cation, normally anions are bigger. Okay. Polarizing means they are going to have ability to distort the ionic, distort the anionic electron cloud. Okay. So the electron cloud, they are going to actually distort like this. They will pull the electron cloud over there. And this happens in ionic compounds. And when this happens, okay, they will give you some sort of covalent property. Okay. It will try to bring them, okay, so that they will have this some sort of sharing of electrons. So distortion. Okay, so polarizing means the cation pull the ion, pull the electron cloud of the anion to itself. Yeah, that is polarizing power. So the more you pull, what happens? Okay, if you have nitrate or carbonate, yeah, so the bonds between the nitrogen and oxygen, because the electrons is being pulled, okay, that bond will become weakened. Okay, if that bond is weakened, then decomposition can happen easily. Yeah, you do not need to require a lot of energy to break the bond. Yeah, so here, because it's bigger, okay, they do not polarize, okay, that much compared to Mg2 plus. Okay, therefore, okay, there is no distortion. Okay, there is no distortion, less distortion, okay, of the NO3 NO3 minus, okay, less distortion of electron cloud. Actually, better to say electron cloud in NO3 minus ion. Okay, so and the bonds, okay, are not weakened. Okay, if the bonds are not weakened, you require more energy to break the bond. Is that okay, Josh?
Yeah.
So if I look at it in form of magnesium 2 plus is smaller. Yeah. So Mg2 plus, they will be more polarizing. Yeah. They are going to pull the electron. Okay, more polarizing because what? More charge, so a smaller. Okay, the nucleus will be able to get the electron from outside. Yeah, so they are going to distort the electron. So the NO3 minus over here, the electron cloud is distorted. Okay, the electron cloud is distorted, and therefore, okay, we use the term polarizing. Yeah, polarizing for the anion. Okay, they will be more polarizing. But when you refer to anion, we say distorted. Yeah, distorted. Okay, don't use the term polarized. Yeah, so it just says the electron cloud is distorted, and the bond between nitrogen and oxygen are weakened and more easily broken. Yeah, so therefore, magnesium nitrate is easier to be decomposed. Okay, so you just need to explain using that. Yeah, but the points, okay, very important. I will highlight the points that might give you the 2 marks here. So you need to mention about this, of course, because they asked which one. Yeah. And then one more mark, okay, must be related to, okay, either you must say they have larger ionic radius, okay, but you need to also mention about either the bonds are weakened together. Normally will not be only 1 point. Yeah, they will join them together. Yeah. So you just need to mention about all this. Okay, larger ionic radius. But the terms, you see, less polarizing, distortion, all these terms, okay, must be mentioned. Okay, Kenneth. Okay, now after decomposition is complete, yeah, 0.01 mole of sample magnesium oxide is taken, okay, and increasing amount of water are added in it, okay, with stirring to until no solid remains. Yeah, okay. So it means that, okay, they are adding, okay, they take the magnesium oxide, they add with water. Yeah, of course, you will get magnesium hydroxide. Okay, they take the strontium oxide, they add water, you will get strontium hydroxide. Now, talking about this, yeah, we talk about the 0.01 later, yeah, talking about this magnesium hydroxide, magnesium oxide, strontium oxide. Okay, we have learned about the solubility. Okay, going down the group, we have learned 2 types of solubility: hydroxide and sulfate. Okay, so group 2 hydroxides going down the group, they are going to be more soluble. Okay, they are going to be more soluble. And group 2 sulfates, okay, going down the group, okay, I told you to remember barium sulfate is white precipitate, yeah. So they are going to be less soluble. Very, very important. Okay, this question is asking why. Okay, it's trying to test why. Yeah, why is this like this? This one we have learned. Okay, using this concept. Okay, lattice energy. Okay, hydration, and your solution. Okay, so there is a formula. Okay, that relates. Okay, lattice energy, solution, and hydration. Okay, which is going to be let your soul go and hide. Yeah, so lattice energy, okay, is going to be always going to be lattice plus solution equals to hydration. Okay, Devan, am I correct?
Yes.
Yeah, so please remember this, yeah, because I think one of the video it was wrong, yeah, so I deleted that video, yeah, but it was not during your batch, yeah, it's actually a video long time back, yeah, but do remember, okay, this one is still correct. Lattice energy, let your soul go and hide, yeah, so yeah, I mentioned like lattice, okay, equals to let your soul go, so soul negative soul plus hydration. Okay, so if you want to remember that, yeah, so whatever it is, okay, please remember this formula. Okay, your solution, okay, your solution, if your enthalpy of solution is a small positive or must be negative, okay, then we say it's soluble. This is very important. Okay, a small positive or generally negative value, they are soluble. Okay, this is very important. Now, using this formula, you do not need to really show the formula at all. Yeah, you just need to know that lattice energy and hydration, yeah, they depend on charge over radius also. Yeah, charge over radius. So we know that more charge, more lattice energy, yeah, less radius, more lattice energy, and so on. Okay, so here, okay, when you go down the group, okay, when you go down the group, for hydration and lattice, okay, we know that magnesium ion, okay, magnesium ion, and strontium ion, okay, let it be for hydroxide or sulfate, doesn't matter. As you go down, we know that the size, okay, the charge is the same, but the size, the ionic radius is increasing. If the ionic radius is increasing, what you should know that, okay, you should know that both your hydration and lattice energy, they are decreasing, okay, they are decreasing, okay, that is very, very important, okay, both of your charge, both of your lattice energy and hydration, they are decreasing, okay, but, okay, depending on OH minus or SO4 2 minus, which one will decrease more matters. Very, very important. Okay, which one will be the dominant factor? Yeah, which is going to decrease more? Okay, is going to be important. So here, okay, if you look over here, if you look at hydroxide, okay, hydroxide, lattice energy decreases more. Okay, I've shared this in your WhatsApp. Yeah, lattice energy decreases more. Okay, compared to hydration enthalpy. Okay, or okay, if you look at sulfate, then your hydration. Okay, your hydration decreases more compared to lattice. Okay, this is going to be your lattice. Okay, decreases more, okay, compared to, no need to know more why, yeah, it's not in your syllabus, but you, when you explain, you have to explain compared to hydration. Okay, so what happens over here, since we are talking about hydroxide, okay, since we are talking about hydroxide, so we will actually focus on the hydroxide. Yeah, we will base our answer on this. Lattice energy decreases more. Okay, when you use the formula, okay, if you want solution, yeah, solution is going to be hydration, okay, minus lattice energy. Okay, even in your exam also, you don't need to specify all this. What happens if the lattice energy decreases more? Yeah, so when it decreases more, the solution, yeah, starts to they are going to become more negative. Yeah, they are going to become more negative. Okay, so you can see here, okay, this makes, okay, the enthalpy of solution becomes more negative, okay, and makes, okay, and makes it more soluble. Okay, why? Because negative means soluble. Okay, negative means soluble. So that this one, okay, is based on, okay, this is based on relevant energy based on the solubility of the product. Okay, solubility of product. So they ask you which sample most water must be added. So of course, most water must be added, the one that is less soluble. Yeah. So you see, you add water, okay, then this is less soluble. So of course, you need to add more water so that they become soluble. Yeah, so that you get something that is more soluble. So the sample, okay, that you need to add most water, okay, is going to be, you say the sample containing MgO. Yeah, don't go and say sample containing MgOH2, because the sample that you take is MgO. Yeah, so because this product is less soluble, then you end up, okay, to make all the solid to dissolve, okay, you need to add more water. So with reference to the solubility of the products, okay, so relevant energy terms and so on, okay, so I'll just try to make it slightly bigger. I think I still put it over here, and you can read. So MgOH2 less soluble requires more water to dissolve. Okay, this is going to be more soluble. Okay, so you explain. Okay, I'm explaining based on OH minus. Yeah, so lattice energy decreases more than hydration. Okay, no need to explain why. Okay, this makes the enthalpy of solution becomes more negative, and because it's negative, it's going to be more soluble. Okay, so the base is from here. Yeah, I will share the PowerPoint slide, okay, that you need to know. Okay, I took the picture the other day. I did share to you also, so that you will refer this. Okay, so I highlighted over there that one. Okay, you can see from the WhatsApp group. Okay, for sulfates, okay, lattice energy decrease smaller. Okay, hydration will be decreasing more. Yeah, so you just need to explain using this. Yeah. So now you see this is going to be related to hydroxides. Okay, they can ask you about sulfates, most probably this year. Yeah, so maybe something related to sulfate. So be prepared for sulfate then. Yeah. So how to remember? Okay, just come up with a way to remember. Yeah, we can't afford to look at the PowerPoint or our WhatsApp message all the time. Okay, hydroxide. Okay, which one decrease more? Lattice. Okay, maybe hydroxide HL. Okay, if you want to remember. Okay, sulfate. Okay, hydration. Okay, SH. Okay, so SH, sulfate hydration decreases more. SH, HL. Up to you how you want to remember. Okay, this is going to be lattice compared to HLH. Okay, okay, for me, okay, maybe I'll just remember one. Okay, for sulfate, okay, I'll just remember like this. Okay, so this is going to tell me, okay, sulfate is going to be for sulfate, okay, hydration decreases more. Yeah, so this one, it will tell me about, okay, hydration decreases more. But you, of course, you need to know, yeah, the base of this. Yeah, you cannot just simply come up with mnemonics and don't know when to apply that. Yeah, so I will move on. Okay, please remember, very important. Yeah, definitely there will be questions, yeah, on this. Okay, please remember. Okay, very important. Now the nitrogen, okay, dioxide, okay, given off by the decomposition. Now let's look at this value, the number of moles. Yeah, strontium nitrate is dissolved in water. Yeah, so the nitrogen dioxide given by 0.01. Yeah, so strontium nitrate. So if you have 0.01, yeah, you have 2 moles of this. Yeah, so it means 0.02 moles. Okay, 0.02 moles. So this is going to be added with H2O2. Okay, and O2 plus H2O2, okay, to give you nitric acid. Okay, if I balance this, okay, I just need to put 2 and then I put 2 there. Okay, if I balance, and I know, yeah, I am producing, doesn't matter whatever value or whatever number there, I am producing 0.02 moles. Yeah, so doesn't matter whether here is 2, 3, 4, 5, 10, 1000, it is going to be 0.02. Okay, not because it's 2 here. Oh, here is 2. Here is 2, 0.02, the same. No. Okay, doesn't matter whatever number there. Okay, whatever that is produced, it will be there. Okay, so which is 0.02 produced, even though here is 4, it must be 0.02. Okay, I hope that is clear. Yeah, so okay, 0.02. So they are asking to calculate the concentration of HNO3, yeah, in this particular solution. Okay, so this one, okay, you are going to get, okay, 2 moles to 2 moles, so must be 0.02 also. Yeah, so you need to find the concentration, like quite simple. Okay, mole per dm cube. So take the number of moles, 0.02. what is going to be the concentration, the volume, okay, 0.15, yeah, in dm cube. Okay, 0.15, you divide, okay, you will get 0.133 of dm cube. Okay, that's the concentration. After that, okay, this is, you need to be very careful with this. Yeah. So they say that the HNO3 present in 25 cm cube of this solution. Yeah, I even almost made a mistake over here. Yeah. Now you see, they have taken like 150 cm cube of the solution. Okay, let's say this one contains 150 cm cube of the solution, and you have calculated, okay, the concentration is going to be 0.133 mole per dm cube. This is not number of moles, yeah, this is mole per dm cube. It means that, okay, when you take 25 cm cube, I think the common thing that we normally do is, oh, this is 150. So we take over here 25. So what we, how many portions? Yeah, we calculate like that, right? So we say 4, 5, 6 portions of 25 is found in 150. So normally what we do, we take the number of moles, we divide by 6. Yeah, which is, I made the mistake. Okay, why? Because I'm not dealing with the number of moles. The number of moles, yes, correct. If you take 0.02, then divide by 6 is okay, which is correct. But you have calculated the concentration. You cannot use this divided by 6. Okay, this is very important. Okay, I divided that by 6. Okay, I'm telling you based on my experience. Yeah, that is wrong. Okay, you cannot divide by 6. Okay, because, okay, that is going to tell us that every 1 dm cube, every 1 dm cube, it contains 0.133 mole. So if you take 25 cm cube, okay, so you just need to calculate for 0.025 dm cube, that is 25 cm cube, right? So how many? So you just need to calculate 0.133 times 0.025 if you want to calculate the number of moles. Okay, if you want to calculate the number of moles. So in this case, I'm not going to calculate number of moles, guys. Yeah, it's just going to be, you just need to take, okay, if you take, okay, 150 cm cube, if this is your concentration, if you take 25 cm cube, your concentration is still going to be 0.133 mole per dm cube. All my explanation is based on this. Yeah, it means the concentration don't change. Okay, number of moles will change. Okay, concentration will not change. Okay, do remember that. Okay, concentration will change only if you dilute. Okay, or only if you dilute the solution. Yeah, you will change the concentration. Okay, by adding water and so on. Yeah, so here they say that they are neutralized, okay, using sodium hydroxide. So first thing, you need to write down, this one is quite simple. Okay, everyone should know this. Okay, NaNO3 plus H2O. Okay, and we know, yeah, I think they made it very simple. So one more. Yeah. So here they neutralize, okay, using, okay, the concentration is going to be 0.125 mole per dm cube, and then, okay, they took 25 cm cube over here. Okay, and then, okay, they are asking you what is the minimum volume, what is this volume, okay, needed, okay, to solve, to get this done. Yeah, but we know the concentration here. Okay, the important thing is to know that the concentration is still going to be this. That is very important. Okay, the concentration is still 0.133. Okay, and then, okay, find the number of moles. Okay, number of moles is 1. Okay, so we know that, okay, if you find the number of moles is concentration times volume divided by 1000. Okay, concentration 0.133 times 25 divided by 1000. Okay, so once you find that, okay, did I count that? Yeah, I think I did. Okay, once I do that, okay, I will get. Can you calculate this? Which one? This one? I think this one, yeah. That 3.325 times 10 negative 3 mole. Okay, you will get this mole. Okay, once you get that, okay, 1 mole is 1 mole. Okay, so the number of moles of this must be the same as the number of moles of this. Okay, so using that, okay, 3.325 times 10 negative 3 must be the same as 0.125 times V divided by 1000, so that the V will be in cm cube. So I calculate 1000 times 3.325 times 10 negative 3, this one and this one will cancel, divided by 0.125. Okay, when I calculate that, okay, I'll get 26.6 cm cube. Okay, that's it. Okay, that's it. So number 5, we will do some other. Efficient element from complexes. So we have molybdenum, MO. It forms an octahedral complex consisting 1 MO atom surrounded by carbon monoxide. Okay, that's ligand. And then the ligand is going to be monodentate ligand. So that is for the first statement. Second statement is going to be, they told about iron forms an octahedral carbon complex, okay, 1 Fe3 plus, and a number of cyanide ions, yeah. So again, cyanide ions are going to be monodentate as well. So define the term monodentate ligand. So when you define, so it's going to be a species, okay, that has, okay, one lone pair of electron, okay, that can actually form, okay, that can form, okay, since monodentate, so one dative bond, okay, to where? Okay, so towards, okay, towards metal or, okay, metal ion. Okay, so this is going to be the definition for monodentate ligand. Yeah, so complete the table by stating the formula and the charges of the complexes described. So they say that, okay, it forms, okay, octahedral complex surrounded by CO. So octahedral, okay, the structure, if you have MO, then the structure will be something like this. Okay, octahedral, up and down. So you can see that there are total of 6, okay, dative bonds. 1, 2, 3, 4, 5, 6 dative bonds. So it should be, okay, the formula should be MO, and then you're supposed to have CO, there should be 6, okay, and then they say it's an atom, so there is no charge, yeah, so something like that. So they mention also iron, they form the same octahedral complex, so they should have the 6 dative bond as well. So Fe, okay, Fe used to be 3 plus, so Fe 3 plus. So cyanide ions is going to be -1, yeah, -1. So you have 6, so that's going to be -6. Then this is going to be +3. The total charge, overall charge, is going to be -3. So you need to show that -3 charge over there. So this is going to be Cn, okay, 6, okay, bracket 3 minus, okay. So the charge they have asked over here, so the charge is going to be 0, and this is going to be -3 charge, okay. Now draw a 3-dimensional diagram to show the shape of this iron 3 complex. So again, okay, you are going to show the octahedral shape because they already mentioned that. So you just need to show something like this, okay. This is going to come to, from the piece of paper, so you can actually show them like this. And you can show the one that is going outside, inside the paper, so something like this, okay. So you can show something like this, okay. And then up Cn down. Okay, so this is going to be the complex is going to be bonded to Cn. So Cn, okay, Cn, Cn, Cn. Okay, or to be exact, okay, maybe I can actually put, okay, because the lone pair is coming from the nitrogen, so maybe I'll just put Cn like this, okay, and then Nc, okay, Nc, Cn, Cn, Cn. Okay, at least something like this. Yeah, this is octahedral, but do remember that they say label 180 bond angle over there, so you can show the 180. Okay, either you can show from here, okay, to here is 180, or you don't want to show that, you can also show any opposite. Yeah, so from here, okay, from here to here, okay, you can actually show that this is going to be 180 degrees. Okay, so that is going to be the 180 degrees bond angle. Now the next question is, an excess of aqueous ammonia is added to copper 2 sulfate solution. Yeah, copper 2 sulfate solution, okay, they are, okay, blue solution. Yeah, because, okay, the presence of, okay, because copper 2 sulfate you're supposed to write as CuH2O, okay, 6 and 2 plus. Okay, that is going to be copper 2 sulfate solution. You can remove the sulfate because that is going to be spectator ion. Yeah, so you can remove that. Yeah, so you can just keep it as like this. Okay, so I will write down CuH2O 6, then 2 plus. Okay, you are reacting with excess ammonia. So if you react with excess ammonia, they have already mentioned that this is the complex that is going to be formed. So you just need to write CuNH3, okay, 4. So you require 4 molecules. So you just put 4 there. And then H2O, okay, there are still 2 molecules of H2O left over there. So previously you have 6 molecules. So you are producing, okay, or you are releasing, okay, another 4 molecules of water over here, so which you're supposed to show them over here. Yeah, so this is going to be the ionic equation for this reaction. So let's move on further. Now explain the origin of color in copper 2 complexes. Okay, do remember, okay, this is going to be, copper is going to be transition element. So, okay, when you explain, okay, you need to mention about, okay, the d orbital splitting. Okay, but, okay, because there is going to be the new syllabus, okay, you need to be aware about certain things. Yeah, so I have written over here. Okay, do remember, okay, because of the introduction of the new syllabus, okay, they want you to use certain terms, okay, which is not found in the marking key here. Okay, but I will just include that as well in the answer. You can see that, okay, the marking key should include, okay, the term, okay, which is going to be non-degenerate d orbitals. Okay, if you look at the normal marking key, they will not mention about that. So d orbital splitting, just like that. Okay, but I think you need to, because of the new syllabus, you need to include the d orbitals. Okay, they split into 2 non-degenerate d orbitals. Non-degenerate orbitals means they have 2 different energy. Yeah, and do remember, copper 2 complexes, okay, they are going to follow octahedral. And do remember, in the new syllabus, they have specified that the octahedral complexes, okay, the non-degenerate d orbitals, you are going to have 2 higher, okay, at the higher energy level. Okay, 2 of the orbitals are going to be at the higher energy level, and 3 of the orbitals are going to be at the lower energy level. So you can include that in your answer, okay, which is going to be 2 non-degenerate d orbitals with, okay, with 2 orbitals, okay, at higher energy level, and 3 orbitals at lower energy level. And you can specify, because we are talking about octahedral. Yeah, if it is tetrahedral, then we are going to have different arrangement, which is going to be 3 orbitals will be higher, 2 orbitals are going to be lower. Yeah, so this one you can just remember. If octahedral, okay, maybe you can remember the shape, okay, the octahedral like this, and then 2 up and down. So you can remember the 2 up and down is going to be, okay, 2 is higher or something like that. Come up with a way to remember or memorize this. Yeah, so this is going to be for octahedral complex. So I'm just specifying over here because they ask specifically for copper 2 complex, which is an octahedral compound. And this electron, okay, from the lower energy level, or the 3 orbitals at the lower energy level, they get excited and promoted to higher energy level, okay, by absorbing the frequency of light. Okay, so you absorb the frequency of light. Okay, once it is absorbed, okay, you are going to see complementary color. Yeah, so that is the origin of your copper two complexes, the color which is going to be blue color, complementary color is seen. Yeah, so in order to get these 4 marks, okay, in the new syllabus, okay, we want to focus on the new syllabus. Okay, please focus on d orbital splitting, okay, into 2 non-degenerate orbitals, 1 mark. Okay, and then you mention also, please mention about these 2 orbitals at higher energy level and then 3 orbitals at lower energy level for octahedral. Electrons gets excited and promoted to higher energy level, okay, by, okay, I think this one is going to be, it can be issued 1 mark, and this one is going to be 1 mark. Okay, frequency of light is absorbed, 1 mark, complementary color is seen, is going to be 1 mark. So here is going to be overall, you can see 5 marks, okay, maybe any 4 from these 5 points or something like that. Okay, so be careful when you answer these kind of questions in future. Yeah. Next question is going to be an excess of concentrated hydrochloric acid, okay, is added to dark blue solution of this complex. Okay, so a new complex Z is formed, the color of the solution change. Yeah, so you want to write down what is going to be the equation. So I'll rewrite this: CuNH3 4 H2O2 and then 2 plus. Okay, when you add concentrated hydrochloric acid, no need to write HCl. I think Cl minus is enough already. Okay, because the H plus is going to be a spectator ion. Okay, once you have the Cl, what you will have, this one you should know, CuCl4, yeah, and then the charge, okay, is going to be Cu2 plus, Cl is going to be -1. If you have 4, -4, yeah, so you have +2, okay, the overall charge is -2, so 2 minus, okay, and you are using 4 Cl minus, so you put the 4 over there. And okay, you are going to produce 4 moles of ammonia, and you are also going to release 2 moles of water. Yeah, so this is going to be the final equation, yeah, that you're supposed to write. Okay, name the type of reaction when Z is formed. So this one is Z, yeah. So name the type of reaction that Z forms from this. So this is going to be ligand exchange. Okay, which is going to be the new ligand is going to be the Cl minus. Okay, it is going to exchange, or they are going to remove the ammonia ligand and water ligand, and you are only going to have this tetrahedral molecule of copper CuCl4. Since I already mentioned the answer over here, state the geometry of that. Okay, this is going to be tetrahedral. Yeah, so do remember, okay, for 4 coordinate bonds, okay, you can have either 4 coordinate bonding like this, like CuCl4. Okay, you can either have tetrahedral or square planar. Yeah, for tetrahedral, CuCl4. Square planar, okay, you can actually have, like, for example, if you have nickel and then Cn4, for example, yeah, if you have something like this. Okay, nickel is going to be +2, Cn is -2, yeah, -1, so you have -4 total, so -2, 2 minus. So this one, okay, it's going to be square planar. Okay, so go and check. okay, but especially if you have CuCl4, okay, they prefer to follow the tetrahedral shape. Yeah, state the color of solution Z. So this is going to be, if you are talking about CuCl4, okay, it's a straw colored solution. So straw color. Yeah, so it's going to be like something like a pale yellow. Yeah, pale yellow. So explain why the color of the solution, yeah, is different from the color of the solution of that. So color of the solution just now, okay, they say dark blue, yeah, dark blue solution. So now the color is going to become like straw colored, yeah, straw color. So you need to tell why there is going to be two different colors. Yeah, no point in talking about d orbital splitting anymore. But yeah, so you need to tell, okay, there is a d orbital splitting, okay, changes. Yeah, it means there is going to be different energy level. Yeah, so there is going to be, you tell that there are changes, okay, there are changes to the d orbital splitting, okay, and okay, and this will cause different frequency of, okay, different frequency of light, okay, is absorbed by what? Absorbed by the electrons, okay, from lower energy level, lower non-degenerate orbitals to higher degenerate non-degenerate orbital. Okay, therefore, okay, different complementary color is seen. So the gap, yeah, d orbital and d orbital, maybe the gap is like this, okay, but now the splitting is different, okay, so the energy being absorbed, okay, so you need to tell, okay, frequency, different frequency of light or energy being absorbed, okay, or energy, okay, absorbed, okay, is going to be different, yeah, delta E, different energy. Because if it is different energy, then you are going to have, okay, different complementary color, yeah, of light missing, yeah. So next, question number 6. An excess of aqueous ammonia is added to a solution, okay, still like something like transition elements, yeah. So you are adding there, okay, to complex ion. This one, cobalt 2 plus, yeah, is always written in this form, yeah. Cobalt 2 plus, okay, you should know is pink in color, yeah. So copper, okay, H2O6, okay, 2 plus, yeah, this is going to be a blue solution, yeah. So this is going to be a pink solution, yeah. So this is something you need to remember. So if you don't remember, I think I'm very sure you remember Cu2 plus, okay, is always blue, yeah. CO, cobalt is always pink, yeah. So this is going to be something that you need to remember, yeah. So that's I think to explore detail about it, this is going to be cobalt 2 chloride paper, yeah, is actually used, okay, to test for water, yeah. So that's why, okay, if you have cobalt, okay, with the presence of water, yeah, cobalt 2 chloride paper, the paper will change from blue to pink, yeah, presence of water. Yeah, that's the reason, because formation of this complex. So anyway, so complete the sentence, okay, to describe the color change that will be seen in this reaction. So this is pink, yeah, this one just now I told you this is pink, okay, you are reacting with what, ammonia. So the color is going to be this one, cobalt with ammonia. So this is going to be straw, yeah, straw colored. So you see just now, the one that is going to be straw colored, yeah, is going to be I think I made a mistake, yeah, this is not straw colored, sorry, okay, this is wrong, yeah, this is wrong, this is yellow, yeah. So this is not straw colored, okay. CuCl4 is always yellow, yeah, yellow, sorry, Okay, so yellow. CuCl4 is always yellow. Yeah, it's always yellow. Yellow color. Yeah. So the one that is going to be straw color, yeah, is going to be this one. This is going to be straw color. Okay, so straw color. Okay, so the color change over here is going to be pink. From pink, okay, they are going to change into straw solution. Okay, straw. So straw is pale yellow. Yes, pale yellow. Yeah, so just now I think CuCl4 better to say yellow, yeah, rather than saying pale yellow. Now, why write an expression for the stability constant? Yeah, stability constant, okay, similar with the normal way of writing, yeah, but stability constant will not include water, yeah, because it's liquid, so it's constant. So we actually include, okay, I'll just put over here bracket, okay, CONH3 6 2 plus, okay, I put another bracket to show that this is a concentration. Yeah, so divided, no water, yeah, no water, okay, product divided by the reactant. So ammonia, I put bracket to show concentration to the power of 6, okay, because we follow here. And then we put this one first, COH2O6, then bracket 2 plus, okay, put the big bracket to show concentration, okay, and this is going to be your stability constant. Now the numerical value of K step, okay, is going to be 7.7 times 10 to the power of 4. If you look at this numerical value, what does it tell us? Yeah? So if you look at this number, so this one is going to be your product divided by, okay, reactant. If your product and reactant, yeah, the concentration are the same, then you're going to get 1. Yeah, you're going to get 1. Okay, so if you have, okay, a number that is going to be greater than 1, then you have 10 to the power of 4 and so on. So it's greater than 1. So what I notice over here is my K step value, okay, is more than 1. If it is less than 1, okay, more than 1 means you have more product. If it is less than 1, you are going to have more reactant. Yeah. So this tells me, okay, more product. Okay, more product. So it means that I can also say that my position of the equilibrium is going to be more to the right. Yeah. So in terms of K stability, we are talking about K step means we are talking about stability. Yeah. So let's actually talk about when they say properties. Okay, let's actually focus more on the stability. Yeah, because there are more information that you can get. Okay, because if it is going to the right, we can say that ligand, okay, ammonia is going to be a better ligand than water. They are going to replace, okay, the exchange of ligand will happen and so on. But, okay, the deduction about property will be more appropriate if I say, because it's a stability constant, if I say, okay, that, okay, because it's going to the right, I just say CONH3 6 2 plus is more stable than COH2O6 2 plus, because, okay, you write down, because K step value is more than 1. Okay, so you can tell that. So that is going to be the answer for this. Now, oxygen can oxidize, okay, this to here, okay, under standard condition in alkaline solution, okay, in alkaline solution. So you need to use this information, okay, and the information for this given, yeah, 0.10, and then we need to look at the information from the data booklet. According to the new syllabus, okay, you are not going to need to have a data booklet, but they will give you all the information. Imagine now the information is given over here, so I already checked the data booklet, so I took this information and I will put it over here. Okay, so if you look at this information, okay, I took this information, okay, based on, okay, they mentioned that it's an alkaline solution, yeah, alkaline solution and oxygen. So oxygen must be there, okay. So I select something that has OH minus, something that has OH minus, yeah. So these are the values, okay, negative, the standard reduction potential, negative 0.08, 0.40, yeah, positive, yeah. So we are going to compare, yeah, whether, okay, this one, they say, can it, they say oxygen can oxidize, yeah. If it is can oxidize, okay, it means that O2 get reduced, yeah. So it means that this reaction, oxygen, okay, when they oxidize, so we can actually just count the oxidation number first, okay, to say, to check, okay, whether we are at the right place over here. Cobalt, okay, if you look at it, yeah, ammonia is going to be the charge, the oxidation number is 0, yeah. So this is going to be +3, okay, +3. And then here, okay, ammonia is also 0, so it's going to be +2. So if you look at cobalt, okay, so cobalt is going to be, in this case, +3 to become +2, yeah. So it means that it's supposed to be the other way around, yeah, the other way around. So what you need to do in order to get this equation to go the other way around, yeah, it means this reaction should not go this way, yeah, it's supposed to go to the left. So in order to go to the left, you need another standard reduction potential, which is going to be more positive than this, yeah. So you need to look for the equation that is more positive, yeah. So here I have two equations. They say can, yeah. So it means I must look for something that is more positive than 0.10. So I ignore this, no need, yeah. This is going to be the one that they meant, yeah. 0.4 is more than 0.1, so that makes that this reaction, so I will erase this reaction first, okay. That will make that this reaction is going to be going to the right, okay, because more positive, okay. So that the reaction above, okay, they will end up going to the left because less than 0.4, yeah. So when you join them together, okay, they want you to calculate the E value, yeah. So if it's going to go forward, then it's plus 0.40. And this one is going to go backwards, so it's going to be plus negative, yeah, negative 0.10. And that will give you your E cell value, yeah, E standard. So which is going to be 0.40 minus 0.10 is going to be positive 0.30, yeah. That is going to be the answer. Make sure you write down positive, yeah, very important. Okay, so positive 0.30. Write an ionic equation for this oxidation, yeah, of CONH3,6, yeah. So it means they ask you to combine the equation, yeah, write the ionic equation. So we know that this reaction is going to go to the right, okay. So we know the this reaction is going to go to the left. So I will actually write down as, okay, I'll remove this a bit. Okay, I'll write down this as CONH3, 6. 2 plus, okay, it's going to give me CONH3, 6, 3 plus, and then plus electron, yeah. Even though we change it, yeah, so I'll just put it here, negative 0.10, okay. When I join them together, the full equation, even though I just need to eliminate the electron, okay, I times everything by 4, okay, do remember the E value, you do not need to times by 4, yeah. So this is one of the common mistakes students do, yeah, just going to be either plus or negative based on the position, but no need to times, yeah, times by 4 and so on. That is for enthalpy, yeah, for this one, no need. So once you have this, okay, you will notice that there are certain things that you can combine, which is going to be this one and this one, okay, will get removed, yeah. So you just need to join this together, okay, which is going to be, you write down O2 plus 2H2O plus 4 CONH3, 6, 2 plus. Make sure your writing is neat so that it's very easy for the examiner to mark. Okay, so OH minus plus 4 bracket CO and H3 6 3 plus. Okay, this is going to be the answer. Okay, the ionic equation. Now predict by selecting suitable data from the data booklet. Okay, whether oxygen can oxidize CO2 plus in acidic solution. Yeah, so in this case, you need to get two data from the data booklet. Yeah, one, they are asking oxidize CO2 plus. It means CO2 plus. Okay, you need to get another equation which is going to be to become CO3 plus. Yeah, so this is going to be plus electron. So you find out, and I have already found out from the data booklet is 1.82. Yeah, positive 1.82. So I write down positive 1.82. And then, okay, when I look at the data booklet under acidic condition, yeah, so there must be H plus. So you see H plus is here, H plus is here, oxygen, oxygen, okay. I have water and H2O or H2O2 over there, yeah. So there are two values, okay, that I can use, okay. So I just need to find out whether, okay, they can or cannot. Yeah. So here, in order, okay, you see they are oxidizing. So it means that this must be going to the right. Okay, because CO2 plus must be going to change into CO3 plus, and this is going to be 1.82. Yeah. So whatever that you have, the equation, okay, must be less than 1.82. If it is more than 1.82, then this one will, the arrow will not go to the right. Yeah, it will go to the left. Yeah, we don't want that. So it must be less than 1.82. So you need to look over here. This is less than 1.82, and this is also less than 1.82. Yeah, so you can use any of this, but when I check the marking key, they have used the first equation. So I will use the first equation also. So you see O2, yeah, plus okay, 4H plus, okay, and then plus 4 electron, okay, it will give you 2H2O, okay, which is going to be 1.23. Yeah, so because this value is smaller than 1.82, yeah, so whether this reaction can or cannot, okay, oxidize, okay, the answer is, okay, in this case they are going to go to the right. The answer is yes, okay, they can oxidize, okay, cobalt 2 plus, okay, in acidic condition, okay, in the absence of ammonia. So it means yes, okay, because if CO2 plus to CO3 plus is going to be 1.82, okay. So if the E value, if you want to follow the E value is going to be, okay, 1.82. This one is going to be less than that, so it should be the other way around. So it's going to be negative 1.23. Okay, if you calculate this, okay, 1.82, 1.23, so this is going to be 9. Okay, this is going to be 5, positive 0.59. Yeah, so this is going to be a positive value. Okay, because it's a positive value, then the reaction is feasible. Okay, feasible. So possible. Okay, possible. Okay, so when you answer, you just tell, okay, because the E value is going to be positive, or you can tell that because this value is less than, okay, less than positive 1.82, therefore, okay, oxygen, okay, can oxidize, okay, CO2 plus in acidic solution. But make sure you select the correct, the correct equation, to do this. Yeah, so that's going to be the answer for that. Yeah, yes. Now number 7, the structure of benzene 1,3-dicarboxylic acid is shown. So this is going to be the structure. So they ask you to state the empirical formula for the benzene. So you just need to do some calculation over here. So the moment benzene itself is C6H6, okay, but the moment there is something is attached to it, then it's going to be automatically one of the hydrogen will be gone. So C6H5. But here There are two, yeah, two. So it's going to be C6H4. Okay, so C6H4. The rest, okay, you need to write down that this one is going to be COOH, yeah? And then this is going to be COOH, so it's going to be COOH. Yeah. So if you want to write it down, you want to write it in molecular formula, you can write down Ca. Okay. Hydrogen 4. This one is going to be 2 hydrogen, so H6. Okay. So oxygen. Okay. 2 oxygen. 2 times 2 is 4. Yeah. O4. Okay. This is going to be my molecular formula. So they want the empirical formula. So empirical formula, when I see here, can be everything can be divided by 2. So it's going to be C4, okay, H3, and O2. Yeah, that is going to be your empirical formula. C4, H3, O2 cannot be divided anymore. Yeah, simplest ratio. Now, benzene 1,3 dicarboxylic acid is an isomer, yeah, of benzene 1,4 dicarboxylic acid. So this is going to be position number 1. Position number 2, position number 3. That's why it's 1, 3. Yeah. So they say that okay, the same molecule can actually form, yeah, another isomer, which is, if I simplify, COOH. This is going to be COOH. Yeah. So these are two isomers can be distinguished, okay, by carbon-13 in the mass spectroscopy. Yeah. So if you want to distinguish this according to carbon-13 NMR, so you look at the number of carbon environment. Yeah. So number of carbon environment, if you want to find out, okay, you it's better, yeah, to look at it, okay, by drawing a symmetrical line like this. Okay, and you can see that this is going to be 1. Okay, 1 environment. This is obviously another environment, number 2. So this and this, they are the same environment, yeah, like symmetrical, and they have the same COOH and so on. So that is going to be environment number 3. Environment number 3. Okay, and then, okay, don't forget about this carbon. This is also carbon, and it's still the same as that carbon. So environment number 4. And this is the same as this. Okay, they can overlap. The symmetric line, symmetrical line will help you to identify this. This is going to be number 5. So how many? Okay, for 1, 3 is going to be 5. How about 1, 4? Same. Okay, if you have something like this, okay, you can draw a symmetrical line like this. Okay. This carbon and this carbon, they are the same, so 1. This carbon and this carbon, they are the same, so 2. This carbon and this carbon, same environment, number 3. Okay. This and this, they are the same, so 4. Okay, there's nothing left. So it's going to be, okay, but do be careful. This one, I almost make a mistake over here. Okay, do be careful that, okay, since the symmetrical line can be also applied over here, okay, this and this, okay, they are also symmetrical. They are the same. This one is also the same as this. Yeah. So there is no 4. Yeah. So it's going to be this one. Okay, it's also 1. Same and same. Okay. So 1, 2, and 3. Yeah. So they have, okay, three carbon environment. Okay, let me check again. Yeah. So this one same as this. So this one should be the same as this. This one should be the same as this. Yes, correct. So 3 carbon environment. Okay. Now, benzene 1,3 dicarboxylic acid can be made by 2-step synthesis shown below. Yeah. So they have 2 steps. Okay. So step number 1, okay, I can see here when I write down, I wrote down already the molecular formula C7. So this one you can get it quite fast also. Okay, this one I told you 1 is substituted, it's going to be C6H5. And then this is going to be carbon COOH. So I can rewrite this into C7. C7H6, okay, and then C6, okay, C7, sorry, C7, okay, and then this is wrong then, okay. I can simplify this into C6, okay, C6, H5, COOH, okay, or you can just change it to C7, H6, okay, and O2, okay. So this one is this. Then after that, okay, what do I notice is, okay, this step 1, suddenly there's going to be increase of 2 carbons. Okay, there are increase of 2 carbons, and there's also increase of 1 oxygen. Okay, 1 oxygen, and also increase of 2 hydrogen. Yeah. So if it is something to do with the increase of carbon, normally we think about nitroxy KCN. Okay, but here, okay, since we are dealing with the benzene molecule, okay, most likely here is going to be, and we are also dealing with oxygen. Yeah, this is going to be something to do with Friedel-Crafts reaction, yeah, which is going to be electrophilic substitution reaction. So okay, in order to get 2 more carbon, okay, I use CH3 COCl, yeah, acylation reaction, yeah, Friedel-Crafts acylation reaction. So you are going to get acyl chloride over here. So I need 2 carbon acyl chloride, and then oxygen. The reason why I selected this again, not alkyl groups, because not halogenal alkane, because I need the oxygen. Yeah, I need the oxygen. So the Cl over there. So this is going to be, once you add, okay, you are going to get this molecule. So you can see here, I rewrote the same thing, and then you will have, okay, the Cl go out, and then you will have COCH3. So if you count this, okay, because there's going to be two substitution here, so it's going to be C6H4, not H6 anymore, and then you have COOH, and we have CH3. So if you combine them, you will have, okay, a total of C9, H4, 5, okay, and then 8, so 8, and then oxygen you have 3, O3. So if you compare, yes, okay, we are having the same, okay. So this is correct. Now step number 2, okay, once you get this, okay, so I will enlarge this. Okay, once you get this molecule, which is compound Q, okay, this compound Q, okay, they are going to be changed, okay, into this, okay. So in this case, ignore, because I think 1, 3, yeah, so maybe this one's supposed to be at position 3, okay, or I can just simplify this. I'll put the COOH here. Okay, so here, okay, I am changing this one, they keep as normal, yeah, and then this one is changing into carboxylic acid. The only way that you can change something into carboxylic acid over here is going to be oxidation. So they are oxidizing this, yeah. Any alkyl groups, any acyl groups or something, they are going to change to benzoic acid, yeah, because of the oxidation. So this one, you just remember this, yeah. So here, okay, if I want to write name the compound P, yeah, compound P is quite simple. Okay, you have carboxylic acid with the benzene, so this is going to be benzoic acid. Yeah. Now explain why, okay, the major product of these 2-step synthesis is 1,3-dicarboxylic acid and not benzene 1,4-dicarboxylic acid. So this one, okay, carboxylic acid is going to be electron withdrawing group. Yeah. So COOH is electron, okay, withdrawing group. And okay, in this case, let's actually focus in this question. Okay, normally if it is electron withdrawing group, then they are going to be 1, 3, 5, okay, directing. Yeah. So in this case, 1 is taken, 3 and 5 directing. Yeah, 3 and 5 directing, 3 and 5. So in this case, they have selected 3. Yeah. So okay, it is position 3 directing group. Okay, so that is going to be, instead of directing it to position number 4, yeah. So that's the major product. So that now the regions used for step 1, okay, they this is correct just now, right? So we use that, okay, and then we use AlCl3, which is our halogen carrier. Now these reaction regions, okay, give rise to this particular ion, yeah, which is our electrophile, yeah, which reacts with compound P, yeah. Name the mechanism of this reaction. So this is electrophile. So we know that this reaction is going to be for benzene related. So always electrophilic substitution. Okay, please remember for alkane, free radical substitution. For alkene, generally, if it is going to be the double bond breaking, then we are talking about electrophilic addition. If you are talking about alcohol or let's say CX, okay, halogen alkane, then we are talking about nucleophilic substitution, SN, yeah. And then we also learn about, okay, aldehyde and ketone. Okay, so aldehyde and ketone, they will undergo nucleophilic addition. Okay, and then now we learn about benzene. Yeah, benzene is going to be, they are going to be electrophilic, okay, substitution. Okay, nucleophilic substitution, nucleophilic addition, okay, electrophilic substitution, and so on. So we have all this, okay, so please remember all this. Yeah. Now, there is another reaction, okay, addition-elimination reaction. Yeah. That one also, please go through it, yeah, which is going to be, yeah, please go through addition-elimination reaction. Yeah. Now, draw the mechanism, okay, of the reaction, okay, using this ion, the electrophile, yeah, with compound P. So here, okay, since okay, I think the product is going to be to give you this, okay, they are going to give the compound Q. Q is going to be this one at position 3, yeah. So I'll just focus on position 3, yeah. So from electron from here, okay, they will attack the carbon over here, okay, and you are going to get the intermediate, which is going to be, we'll draw like this, okay, and then plus. So this is C. I'll try to match the question itself. So H. So this one, okay, you are going to have hydrogen and then C double bond O CH3. So what is going to happen next is going to be this one will come in, okay, the 2 electrons from there, and they are going to form this one again. So double bond O OH, okay, at this position C double bond O CH3. Okay, so that's all. Yeah, so they will also give you the H plus. Yeah. So anyway, suggest a region and conditions to convert compound Q, yeah, this compound, into benzene 1,3-dicarboxylic acid. Do remember just now, yeah, any alkyl compound, alkyl benzene or anything, they are going to be converted under oxidation. Yeah, you oxidize, but the oxidizing agent that we use is going to be KMnO4. The difference, okay, with the others is going to be you put in alkaline condition first, okay? Alkaline condition, you boil, yeah, boil or heat, okay? And then, okay, you add, okay, into acid. So So here, I'll put it here, then acid, okay, then, okay, it must be also boil and heat. Okay, so the difference is normally when we do oxidation, we just put acid, okay, potassium manganate, then acidified potassium manganate. But this one is alkaline first with the presence of alkali, and then you add the acid. That's going to be slightly different for this kind of compound. So next question, okay, alanine. They have given you all this information, so no need to refer to the data booklet. So alanine, okay, so generally when you look at the amino acid, okay, amino acid, they are going to have C, and then they will have COOH, and then they will have NH2, and then they will have the R group, the H, and the R group. Okay, the R group is the one that will change. So here, okay, the R group for alanine, okay, is going to be CH3. You can see from here. Okay, so that is going to be the R group. Okay, so if I follow here, okay, so if I copy this, okay, so for alanine, okay, I can just change this one, okay, into CH3. That is alanine. And then for glutamic acid, okay, if I put over here, okay, glutamic acid, okay, the R group, you can see the R group. This is NH2, okay, H, and then CO2H. So the R group is CH2, CH2, CO2H. That's going to be the R group. So this is glutamic acid. So now they are asking you to draw, okay, for this alanine, okay, it actually says two optical isomer, of course, okay, because they have the chiral center over there, 4 different groups. So draw 3-dimensional structure for these 2 optical isomer. So when you draw, okay, please remember you put C1, okay, one line, another line. This one always, okay, you have 2 lines over there. So you have CH3. So I put NH2, okay, and then the third line, okay, you draw, okay, coming out from the paper. So you just need to do like this, okay. So you can put H over there, okay. The one that is going behind, okay, you can either use this way, or you can add dotted line, okay. So I just put like this, okay. Okay, this is going to go behind the paper, which is going to give me the COOH. Okay, so the optical isomer is the 3-dimensional shape. So I just draw. Okay, you can just put carbon. Okay, and then you can put, okay, the mirror image. Okay, so you can just copy the same mirror image. Okay, so just put like this. Okay, so this one is going to be like this. Okay, if you want, okay, this one, put like this. Okay. So this is going to be COOH. This is going to be hydrogen. This is NH2. This is going to be CH3. So this is going to give you, okay, the optical isomerism. Now the proton NMR, okay, of either alanine in D2O. This is heavy water. So if you have heavy water, okay, the OH bond, okay, and then the NH bond will not be shown because rapid exchange normally will happen, okay, between the hydrogen. And then because of that rapid exchange, okay, because the hydrogen is going to be replaced by deuterium. Deuterium is going to be hydrogen 2, so it's even mass, okay, it's not going to be detected or give any NMR spectrum. So that peak will be disappearing. So here they ask you whether this is the spectrum for alanine or glutamic acid. So we need to find out. This is going to be proton NMR. So we just can actually find out, okay, how many different hydrogen environment are there first. So that's going to be something that we need to do first. Okay, so if you look at hydrogen environment, do remember the nitrogen and hydrogen will not be shown in your NMR, okay, and this one will not be shown as well. So no point in identifying that. Okay, but I know that this is going to be one environment, Okay, and then the CH3, each of these hydrogen, okay, will be one environment, but they are the same. Yeah, so this hydrogen, this hydrogen, this hydrogen, they are the same environment. So two. Okay, so there are total of 2 hydrogen environments, okay, in alanine. So if you look at glutamic acid, okay, we know the same, okay, no, not detected, no point of looking into that, okay, but I know this is going to be 1, and I know that, okay, these 2 hydrogen is going to be 1 environment. These 2 hydrogen is different also, yeah, that's going to be another 1 environment, okay, and this one will not be detected. So total, you are going to have 3 environment, okay, 3 environment. So do remember this one is going to be C double bond OOH, yeah, so not detected. Okay, I hope you can understand why. So once you get that, okay, there are 3 environments. So you see, if you have glutamic acid, then you must have 3 peaks. Yeah, if you have alanine, 2 peaks. So I know for sure this is going to be alanine because there are 2 main peaks over here. Okay, so I just need to confirm, yeah, whether this is alanine or not, yeah, by looking at the splitting. This is going to be high resolution NMR, yeah. So if you look at this, okay, this one there are going to be quartet, yeah, so 4 splitting, so quartet. So if you have quartet, it means that your neighboring carbon or adjacent carbons hydrogen environment, yeah, there are 3 other hydrogen, yeah. So you can see this is the neighboring carbon, and then there are 3. So it means that this quartet belongs to the hydrogen attached, okay, attached to CH3. Okay, so hydrogen attached to CH3, which is going to be, okay, which is going to be having 3 hydrogen, okay, in the adjacent carbon. So that gives you the quartet. Yeah, so this one, okay, is belongs to, okay, this hydrogen, okay, attached to CH2 and then attached to CH and so on. Yeah, so this COOH and NH2. Yeah, so it means that, okay, why? Because you see the adjacent carbon, yeah, the adjacent carbon, okay, the adjacent carbon has 1 hydrogen attached to it, okay, so that's why they form duplet, n plus 1, yeah, duplet. So this is the reason. So explain your numbers based on the number of peaks and splitting pattern. Alanine, because 2 peaks, okay, and 2 hydrogen environment, whereas okay, glutamic acid has 3 hydrogen environment and should have 3 peaks. Okay, that's 1. So alanine has peak at maybe here 3.7, maybe 3.7. So it has what kind of peak? Quartet. Because the adjacent carbon has 3 protons. And then you say alanine also has duplet or doublet. Yeah, I think not duplet, doublet. Doublet, peak, at 1 point, maybe I'll just put 1.5 here, at 1.5, because the adjacent carbon has 1 hydrogen. Okay, so that's the explanation. Yeah, so enough to give you the 3 marks. Now the next question is the mass spectrum of glutamic acid, okay, is obtained. So state the ME value for the molecular ion peak. So you just need to join all of them together. Yeah. So calculate. Yeah. So if I calculated here, okay, this is 16 CH. Okay, that's going to be 13 COOH. Okay. So this one is going to be 45. Then CH2, 14, 14, and then COH. Yeah. So I just need to add all this 16, okay, plus 13, plus 45, 14, 14, 45. So this is 90. So 29. This is 28, 7. So that's going to be 147. Okay, 147. Now the spectrum has peaks at MOE 88. So I think if you write it down like this, it's much more easier to get the answer. Yeah, 88. Yeah, 88. So you just need to see, yeah, from where I get 88. Okay, so if I put 16 plus 13, so that's going to be 29. Okay, if I have 45, okay, that's going to be 74. Okay, if I include everything, yeah. And then this CH2, so if I put 4, so that's 88. So up to here. So up to here is the one that will give me 88. So I just need to write down NH2, okay, CH, COOH, CH2, and then put plus. Yeah, that's 88. So now 131. So this one is 88. So 131. How do I get that? So this one, the 147 is going to help us with that. Okay, 147. If you want 131, what's the difference? You find out first. Yeah, so bigger number. Yeah, so 6. So 16. So the difference is 16. So you can just look from here. 16, this is 16. So it means that it must be something that doesn't include that NH2. Yeah, so you just need to draw from here all the way to here. Okay. So here, okay, I put CH, you see CH, and then CH2, CH2, COH, and then COH, and then plus, okay, because this is plus here. So that is going to be the structure of ions responsible. Yeah. So at pH 11, okay, alanine exists, okay, in this form, okay, and so normally, yeah, they exist in zither ion, yeah, but because of the buffer solution, then they are going to give you different charges. So you have this, okay, glutamic acid. They have given you all this, okay, but from here, what I notice is this is -1 charge, okay, this is going to be -2 charge. So a mixture of alanine and glutamic acid at pH 11 is subjected by electrophoresis. Yeah? So state how the mixture can be maintained at pH 11 during electrophoresis. So if you want to maintain, yeah, so the only way is to use the buffer solution. Okay, so then the pH will remain so fixed at 11. So and then draw a fully labeled diagram, okay, that can be used to carry out electrophoresis. So this one you can find from the Passy papers and so on. So I've taken from one of the Passy paper. Okay, this is actually suggested by the CIE, yeah, Cambridge. So you can draw something like this, okay, or you can simplify your diagram, okay, depending how you want to draw. So like for me, I will just draw like this, okay, so DC power supply. And then, okay, I will draw maybe 2 trays. Okay, so I'll just draw 2 trays. Okay. And then I put the filter paper or the gel, okay, here. And this one will go here, go here, like filter paper. So there is going to be buffer solution there. Okay. Buffer solution there. So the DC power supply, okay, you just put here, DC power supply, put here. Yeah. So the circuit is complete. Yeah. So you just need to label. Okay. So filter paper, soaked buffer 11, pH 11. So here you put the amino acid here. Yeah. So you see you are going to put a mixture of alanine and glutamic acid. So you just need to tell, okay, mixture of amino acid. So it's going to be glutamic acid and alanine. Okay, so think here, okay, you just put the glass slide. Okay. So this is going to be the setup. Do remember, just put the positive and negative. Yeah, doesn't matter where you put, but later when you have the results, that you will have, okay, accordingly. So in this case, this is going to be negative charge. They will move to the positive. So here, identify the electrode each amino acid will go. Yeah, so I told you this is alanine is going to be -1. Okay, this is going to be glutamic acid is -2. So both of them, they will go to the positive electrode. Okay. In a particular electrophoresis experiment pH 11, glutamic acid, they travel 3.4 cm. Alanine travels shorter distance. Explain the factors. There are two factors normally. Okay, one is the charge. Okay, another one is the MR. Yeah. So these are the two factors. But in this case, okay, I do see that glutamic acid 3.4. So glutamic acid is actually traveling far. Yeah, further. So if glutamic acid is traveling further, I think most probably because of the -2 charge. Yeah. So I'll just say basically depends on, okay, depends on charge and MR, okay, relative mass, okay. So or relative molecular mass. Okay, relative molecular mass. Okay, but in this case, okay, when I see here, okay, this alanine is smaller. Okay, MR is smaller compared to this molecule. So you can, if you want, you can count. Yeah, but I can see here there's a lot of carbon here, so the MR is greater over here. So supposed to be, okay, alanine is smaller. Okay, and if MR is smaller, normally they will travel further. Yeah, but in this case, they travel shorter distance. So the main, I can say that the major or dominant, okay, the dominant factor for this is charge. Okay, because glutamic acid has -2 charge and travels further than alanine. Normally, amino acid with lower MR will travel more, but in this case, okay, glutamic acid travels or separated further because of the larger charge. Okay. If you want to include that they are going to the positive electrode, you can include, but I think they already know over here. Yeah. So that's going to be the answer for this. Yeah. So the next question, okay, butylamine, yeah, butylamine, okay, they can be synthesized from different organic compounds by using suitable reagents. Yeah. And each of the reaction involves one step. Okay, complete the table to describe 3 different syntheses. Yeah. So it's going to be 3 different syntheses and 1 step reaction. So don't get confused that you can actually use the 3 steps to achieve this. Yeah, that is wrong. Yeah, so you need to have 3. I think the question means that they want 3 different methods. Yeah, to synthesize this butylamine. Yeah. So one of the 3 syntheses should involve nucleophilic substitution. Nucleophilic substitution, it must be involving OH or anything that involves the CX, halogenal alkane. Yeah? So then the starting compound for each of the syntheses should contain different functional group. Different regions should be used for each synthesis. So here, okay, I think first maybe I'll try to complete this one. So maybe let's try with maybe alcohol or halogenal alkane. So if you look at nucleophilic substitution, that gives you amine. I think the reaction with ammonia. So maybe halogenal alkane. So I will select CH3, CH2, CH2, CH2Cl. Yeah, that is going to be the organic compound, halogenal alkane. And the region is going to be, they are going to react with ammonia, excess ammonia. Okay, excess ammonia. Okay, excess ammonia. And then the pressure must be higher, so under pressure. Okay. Under pressure, and this one is quite special. Okay. This one, okay, must be heated. Okay, heated in a sealed tube. Okay. So that's going to be the first one. Okay, the second, okay, the starting component, okay, should be so that is already done for this. Okay, then different functional groups. So another one maybe, okay, when we look at the production of amine, okay, you can also have something to do with amide. Yeah, amide, you can what we can do with the amide, you can reduce amide to become amine. Yeah, so maybe I'll just write down CH3, CH2, CH2, C. So C double bond O, CO, and H2. Yeah, so this one is amide. Yeah, so this amide, okay, you need to use the reducing agent. So the reducing agent is LiAlH4 in dry ether. Okay, and then this one I think you need to heat. Yeah, so LiAlH4 in dry ether, and then you heat, you are going to get, okay, the amine. Yeah, you're going to get amine. Now the next one is going to be related to if you have nitrile. Yeah, that's another one. If you have nitrile, you can also reduce nitrile. Rather than reducing amide, you can reduce nitrile. So CH3, CH2, CH2. So this one is CN. Okay, so 4 carbon. Okay, must have 4 carbon. So this nitrile, okay, you can either use this as your reducing agent. Okay, but because they say different regions should be used, I will not use, okay, this region, because I think because they want different starting organic compounds, so that is okay. Different regions, so we still need to maintain different regions. So if you look at this reduction of nitrile, okay, they can be also done, okay, using hydrogen gas, okay, with nickel catalyst, okay, and then you heat up. Okay, so you can heat them up, you can actually get the reduction as well. Okay, so this is going to be the reactions. Okay, now the next part is compare and explain, okay, the relative basicity of ammonia. So when we talk about basicity, okay, basicity is going to be depends on the availability of the lone pair of electrons to receive or to bond, okay, with proton. Okay, so that is going to be the basicity. So all of them, okay, all ammonia, butylamine, okay, phenylamine, yeah, they all have, okay, all the ammonia, butylamine, and phenylamine has nitrogen which has one lone pair. Okay, so they are available for bonding. Yeah, but the one if you look at ammonia, okay, ammonia, so ammonia normally will come in the middle. Yeah, ammonia will be middle. Butylamine, okay, is going to be C4. Yeah, C4, or just CH3, CH2, 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 then NH2. Yeah. So this is butylamine. So butylamine, okay, contains the R group. This is going to be the R group. So R group, what they do, there is a lone pair. Okay. The R group, okay, has, okay, they are going to be electron donating group. Yeah, they are going to be electron donating, or you can say it has a positive inductive effect. Yeah. So you can say that, okay, butylamine has alkyl groups which has positive inductive effect. Okay, they are going to donate the electron, and the electrons at nitrogen atom are repelled to make it more available for bonding. With H plus. Okay, so that's the first part. They are going to be more basic. Okay, therefore, okay, the one that is going to be more basic than ammonia is going to be butylamine. Okay, ammonia is like normal, yeah, that's going to be the standard. So the least basic is going to be phenylamine, because the phenylamine, okay, they contain also the lone pair, okay, but okay, the lone pair is going to be delocalized into the benzene ring, because the lone pair, okay, of the electron, okay, they are going to overlap with the pi bonding system, yeah, with the p orbitals in the pi bonding system, okay, making it more stable. So that electron will be less available for bonding. So we need to put it down over here. So phenylamine, the lone pair of electrons in phenylamine is delocalized into the benzene ring or overlap with the p orbitals in the benzene ring, okay, and becomes less available for bonding. Okay. However, I've put all this information in a simple form here. Okay, I'll just pass you the PDF later. Okay, so you can refer over that. So all this, okay, will give you the 4 marks. Okay, next, the last question. Now complete the table to show the organic product. Okay, the answer is organic product. Yeah, so contains carbon. Yes, from each of the reaction of phenol. Yeah, so phenol, when you react with sodium hydroxide, phenol do react with sodium hydroxide. They will give you. Yeah, so if I write it down over here, phenol. Okay, when they react with sodium hydroxide, they will give you sodium phenoxide. Okay, O minus and A plus and water. Okay, so the structure of the organic product, okay, you can just draw this one. Okay, O minus, you can draw, okay, because they didn't specify. Okay, you can draw, or if you want to write it down, you can just write down C6H5 O minus. Yeah, so any, yeah, you can leave it. Okay, water will not be an organic product, so you no need to mention that. Yes, phenol and sodium. Yes, phenol and sodium, they are going to react. Okay, so same, they are going to give you sodium phenoxide. Okay, and then they are going to give you half H2, hydrogen gas is given. So here, similar, you draw O minus. If you want to include Na plus also can. Yeah, so still can. Okay, so I didn't include. Okay, should be okay. Yeah, if you want to include Na plus, then make sure you put Na plus. Okay, you put Na plus. Okay, this one Na plus. So it's okay. So I'll include that. So if you put this C6H5 O minus and A plus. Okay. Now this is going to be a diazotization reaction. Phenol, okay, reacting with this, okay, this molecule, diazonium. Okay, so you are going to get, okay, the orange dye. So sodium hydroxide at 4 degrees Celsius here. So I will draw directly, okay, maybe here, maybe I'll just put OH. Okay, then you react with this N2 plus. Yeah. So what will happen? Okay, this one, okay, they will stay. Okay, so this one of the hydrogen will be gone. They will form bond over here. Okay, so what will happen? You are going to get, I'll straight away draw here. Okay, you will have OH here. Okay, position number 4 will be activated. So you will have nitrogen and then double bonds, and then you will have this. Okay, this is going to be the molecule, okay, for, that will be formed, which is going to be the orange dye. Okay, but I think no need to write that. Okay, so this is going to be the diazotization, and then they say excess of phenol. Okay, phenol, they do react. So if I put it separately, phenol, okay, phenol, okay, when you have OH, okay, when you react, okay, this applies for ROH also. Okay, when you react with the C double bond OCl, okay, the R, okay, acyl chloride, okay, they do react where they will give you like some sort of they will give you ester. Yeah, they will give you ester. So you are going to get, okay, I will just write down here O, okay, and then C double bond O R, okay, and then HCl is given up. Okay, if you look at ROH, they are going to follow the same thing as well. Okay, this one and this one will come out as in form of HCl. So you will have R, let's say R1 and R2, R1 with C double bond O, then R2. Yeah, this is also ester. So here, in this case, if you have excess phenol, then left and right, yeah, this Cl and Cl will react. So it means that, okay, if I draw this one like this, okay, O, okay, H and Cl will be gone, so they will join with C double bond O. Okay, then join with this. Okay, C double bond O. Okay, Then join, the Cl will be gone, so join with another phenol. Okay, this is what you are going to get. Yeah. So identify two reactions from the table which ethanol will behave in the similar way as phenol. Yeah. So it's quite simple. Yeah. Ethanol do not react with sodium hydroxide. Do remember that ethanol is not acidic enough. Yeah. So they are not going to react with sodium hydroxide. Okay. They do react with sodium. Okay. Ethanol will not undergo diazotization reaction. Ethanol do react. Okay. You see just now, they will undergo esterification reaction. But this reaction, do remember this esterification reaction with normal alcohol and carboxylic acid, they need concentrated sulfuric acid and heated under reflux. But this one, it happens at room temperature. And this is very interesting also. It's going to be room temperature. So because ethyl chloride is very reactive. So therefore, okay, you are going to have, okay, the reaction 2 and 4. Okay, so we identified that. Okay, so maybe I'll just say reaction with, okay, with sodium and reaction with, you can draw, yeah, if you don't know the name. Okay, just draw. Okay, so I'm going to, okay, just put this here. Will do. Okay, so that's all. Okay, that will be completing this particular question, up to 10 questions. Yeah, thank you everyone. Okay, see you.